Vabbè, fuori alla...
Sì, io vado fuori.
Magari.
Ma io non riesco a vedere niente su YouTube.
Benissimo, cioè non ho dei codi.
Mi confermi che la live è partita su YouTube? Ah, ok. Io non vedo niente. Ah, ecco, mi vedo, perfetto. Sì, sì, è arrivato adesso, tutto bene. Bisogna soltanto controllare l'audio. Vediamo. Come facciamo a controllare? Ci vuole qualcuno che parli?
Aspetta.
Prova audio. Si sente? Ok.
Tirate un po' con la videocamera.
Aspetta.
No, è più orientabile di
Abbiamo
questo.
due posizioni, due che è questa qua, per quelle persone di qua, e uno per chi parla di qua.
Il pubblico... Se no, poi mano al mezzo puoi fare pure...
Però quella è il range un attimo di...
Prima proprio toccare la... Se no devi andare là a toccare e muovere.
Cioè la devo muovere la illuminazione, sì.
Cioè, la spostiamo.
Qua cioè, se la metto qua si vede. Cioè, da qua non
Può continuare a usare. Una e due sono le posizioni che io ho salvato. Se tieni premuto
tanto così vedi. Magari puoi vai. No, è... Questo è... Vabbè, magari poi la giriamo un altro poco. Girare lo schermo?
Ti puoi spostare un po' male.
il problema è che poi togliamo.
Va bene. Vabbè, ma così si vede però.
No, è solo gli speaker.
No,
poi dall'altro lato per girare facciamo così per vedere gli altri. Quando parlano gli altri. Cioè mettiamo questa qua per gli altri. E poi lo speaker.
Metti un attimo la prima.
Questa è solo per
la prima. E questa qua, la seconda e questa qua.
Non tenere premuto che ti cambia posizione. Vedi dove arriva. Piglia solo una fetta di cucurione, perché altrimenti poi arriva massimo fino a Davide.
Però scusa, mi sembra che
la seconda e questa qua.
Non tenere premuto che ti cambia posizione.
Ma tanto è la rotonda il problema. Poi dopo
piglia solo una fetta di cucurione,
cioè
perché
se uno
altrimenti poi arriva
qua,
massimo qualcuno viene
però scusa, viene
la seconda e questa qua.
non tenere premuto che ti cambia posizione.
ma tanto è la rotonda il problema.
Vabbè, metto a giocare io con
piglia solo una fetta di cucurione,
cioè se
perché
uno
altrimenti poi arriva massimo qualcuno viene
però scusa, viene
la seconda e questa qua.
non tenere premuto che ti cambia posizione.
ma tanto è la rotonda il
Vabbè, metto a giocare io con
piglia solo una fetta di cucurione,
cioè se
perché
uno
altrimenti poi arriva massimo qualcuno
però
viene
scusa, viene
la seconda e questa qua.
non tenere premuto che ti cambia posizione.
ma tanto è la rotonda il
Vabbè, metto a giocare io con
piglia solo una fetta di cucurione,
cioè se
perché
uno
altrimenti poi arriva massimo qualcuno
però
viene
scusa, viene
la seconda e questa qua.
non tenere premuto che ti cambia posizione.
ma
tanto è la rotonda il
vabbè, metto a giocare io con
piglia solo una fetta di
YouTube. No, ma aspetta, se uno
altrimenti poi arriva massimo qualcuno viene
però scusa, viene la
non tenere premuto che ti cambia posizione.
ma tanto è la rotonda
vabbè, metto a giocare io con Su YouTube, no, ma aspetta, non hai il gruppo di microfoni.
Ok.
Ok.
Ma tu lo vedi da qua che sta pigliando l'audio.
Che ancora sei sempre benissimo.
Ma forse stavano dicendo qualche...
Non si capisce bene.
Puoi vedere se sta la
Se sta?
Se sta la barra.
Vai.
Verso me che stavo parlando di altre cose.
Casa.
Sì, sì.
Vale?
Sì, sì. Si muove quantomeno.
Ok.
Ma è zero, vabbè. No, no,
Perché ho spento il microfono. Perché diciamo la cacciata. No, io voglio.
Va bene, ok.
No, tutto bene, anche noi, quindi perfetto così, grazie. Pure a voi, grazie.
Sì, però. Credo. Ah, ma questo qua non è la posizione fatta.
No, è un po' più di qua perché lo speaker solo quando si alza il fanno, ok, non da questo lato.
Vabbè, chi Massimo?
Questo è il massimo.
Questo è il massimo.
Non posso andare, vedi, sto già premendo.
Allora, faccio questo qui. Premi 2.
Ah, per andare sull'altro, dici. Guarda, io due la metterei forse per un po' di così,
Perché non so se poi magari si fosse poco più dietro qua sei piace. Quindi ho dato un po' di gioco.
Vabbè, al limite la spogliamo poi.
Metti un po'.
Uno in così.
Ok, questo sposta un poco più a destra. Questo lasciamo sulle persone normali.
Ah, io ho capito, cioè lui non lo vuoi lasciare su questi qua.
Esattamente. Quindi premuto uno sì. Ok, così si salva la posizione.
Quindi poi quando parlo lo speaker mi muove.
Esattamente, se si alza e si muove, si sposta normalmente.
Quindi poi fai uno per chi parla di qua e due per chi parla di là.
Esattamente. Forse uno spostiamo un po' più a destra. Esatto. Uno si è, poi al centro chi è? Riccardo? Se io sto...
E comincio a muovermi. Più così forse.
Guardi.
27 ha salvato?
Sì.
Ok, perfetto. Abbiamo una cinematografia.
Non credo, però se già funziona, vabbè. Ok, lo metto qua, dai.
Però mi sembra anche tu. Sta facendo della richiesta di spazio. Cambia possono essere contanti. So Andrea c'è che sa anche
Vabbè, stanno là sopra il server. No, è perché le prese vanno riportate. Perfetto. Ha detto, visto che oggi c'è fino alle 5, se finiamo alle 4 possiamo chiamarci. Non lo fa. Vabbè, ricordiamoci.
allora sì, che credo un passaggio da giovane. Anche questo adesso perché
No, direi con questa seduta, tanto benvenuti a tutti, sempre sono Matteo Massicci, abbiamo la divulgazione del Centro Nazionale ISC, che è genere di ricerca, nato con il PNR in fisica e quantum computing, che ha iniziato il calcolo che è presentato ieri in una prima giornata un po' più aperta al pubblico. Oggi questa è una giornata un po' più tecnica, sempre forse molto più interessante per tutti di voi. E vabbè, adesso poi valuterete, ma comunque li conoscete tutti, quindi a me stava dato solo il compito di aprire le danze, poi ci la parola ai nostri ospiti. Sì, è un po' ballerino, scusate, spero che mi sentiate tutti, spero che mi sentano anche i relatori che sono collegati da remoto. Ancora benvenuti a tutti, ritrovo tutte le facce che c'erano ovviamente già ieri, gli altri invece ci hanno raggiunto per questa giornata di oggi, in cui andremo un po' più nello specifico su quello che è il sistema italiano del calcolo quantistico e tutto quello che è il sistema quantico in Italia e su quello che poi ci aspettiamo potrebbe essere questo sistema, questa filiera che si vorrebbe costruire in Italia per l'appunto. Non rubo più tempo, lascio direttamente la parola agli ospiti che ci hanno raggiunto per dei saluti. Sono già presenti con noi Lorenzo Marcucci, Università di Napoli, delegato alla ricerca, Fabio Villone, di Federico II, sempre direttore del Chieti, Domenico Accardo, direttore del CERMA, e Antonio Pascapè, delegato alla terza missione. Lascio la parola intanto a Lorenzo Marcucci, Lorenzo Marcucci per i saluti e grazie. Può parlare anche per questo indicato su questi perché sentono poi anche online? Sì, credo di sì. Sì, buongiorno a tutti. Diciamo, insieme ai colleghi del tavolo abbiamo il compito innanzitutto di darvi il benvenuto e benvenuto anche a nome di tutto l'Ateneo. Io poi sono anche membro di questo dipartimento, quindi sono particolarmente coinvolto, ma questo ruolo, diciamo, saluto a nome dell'Ateneo. Oggi, come sapete, continuiamo questa giornata di inaugurazione di questo calcolatore computer quantistico. Mio figlio mi prende in giro che io ancora dico calcolatore, da prima forse. Questo computer quantistico a 24 qubits che è stato installato nei locali del Dipartimento. Innanzitutto qualche parola sulle prospettive, volendo dal punto di vista dell'Ateneo, questa milestone che oggi celebriamo. È ovviamente di interesse per la fisica, per la comunità di questo dipartimento, ma in realtà ha un'importanza molto più ampia, tant'è vero che vicino a me c'è anche per esempio il direttore del CESMA, del Centro di Metrologia dell'Ateneo, e in generale la computazione quantistica è una prospettiva tecnologica di grandissimo interesse per molte discipline dell'Ateneo, che spaziano dalla fisica, una certa parte importante dell'ingegneria, in particolare ingegneria dell'informazione, antropologia, la chimica potenzialmente di grande interesse anche per questo. Il computer quantistico è, se vogliamo, una delle frontiere tecnologiche che attualmente si sta tentando di sviluppare a livelli sempre più alti e che promette potenzialità, diciamo, potenzialmente senza limiti in certi ambiti, anche se finora gli algoritmi quantistici consentono delle cose più specifiche, ma comunque molto importanti, molto interessanti. La presenza di un computer quantistico, diciamo, di 24 qubits, quindi piuttosto interessante anche per cominciare a fare delle simulazioni di un certo rilievo, non facilissime da simulare classicamente, al limite, diciamo, delle potenzialità di simulazione classica. È un'opportunità quindi di crescita notevole sia per il Dipartimento che per l'Ateneo, non solo per la ricerca, ovviamente per la ricerca, ma io direi anche per le potenzialità di formazione, di
insegnamento agli studenti e anche di formazione di figure, diciamo, di ricercatori di informazione, di tecnologi, che poi potranno applicare queste conoscenze anche nel mondo reale, nell'industria. Questo aspetto forse è addirittura più rilevante perché diciamo, esperimenti su computer quantistici si possono oggi fare anche in remoto, quindi la possibilità di farli in sede è cruciale per imparare effettivamente, diciamo, anche gli aspetti di hardware che sono connessi con il funzionamento di un oggetto del genere. Io vorrei anche ringraziare chi ha reso possibile questo passo avanti così importante per noi, a partire innanzitutto volendo dal piano di nazionale di ripresa e resilienza, il PNRR, che rende possibile l'acquisizione di questo oggetto così complesso e importante, in particolare in questo caso nell'ambito del Centro Nazionale di High Performance Computing e Quantum Computing, e ovviamente attorno a questo centro, che è quello direttamente coinvolto nell'istituzione di questo computer, ci sono poi altre iniziative PNRR fortemente interessate, come per esempio il partenariato NQSDI, National Quantum Science and Technology Institute, che pure è finanziato anche qui e che guarda questa risorsa con grande interesse. Quindi questo è uno degli esempi più eclatanti di come il PNRR ci sta rafforzando e sta rafforzando le nostre prospettive. Poi voglio ringraziare invece gli artefici di questa installazione, di questa messa in funzione di questi quantum computer, cioè il gruppo del professor Tafuri, tutti i suoi collaboratori che hanno reso possibile questa cosa. E io mi fermerei qui. Quindi ancora grazie a tutti per essere presenti, grazie agli ospiti che parleranno e agli altri che ascolteranno, e buon proseguimento. Passo la parola al
buongiorno a tutte e tutti. I due delegati non sono compatibili, come vedete.
Stavo cercando
No,
di
no, non vorrei. Ci riprovo, buongiorno. Io riprendo esattamente, buongiorno anche a chi ci segue da remoto, un amico Popes. Hai ripreso a correre? Ok. No, però sto rumore è fastidioso.
Vuoi provare a prendere tutto?
Allora, proviamo così va bene?
Sì.
Oh, sì, comunque, vabbè, deve andare bene per forza. Io vi proverò a dire veramente poche cose e mi scuso sin da adesso. Francesco Giampiero, troppo alle 10 c'è un altro importante momento di inaugurazione, parte stamattina un festival sull'antimafia sociale a circa 50 metri da qui, quindi questo vi facilita la logistica, ma vi fa essere molto maleducato con lui, perché purtroppo io dovrò spostarmi per andare lì. Ma mi faceva molto piacere essere qui, perché ho accettato l'invito per una serie di motivi. Io sono molto vicino a queste tematiche tecnologiche, ma non è questa solamente, diciamo, il motivo della mia presenza qui stamani. Riprendendo un po' quello che diceva Lorenzo, con cui stiamo provando a fare un lavoro molto sinergico in Ateneo sulle conoscenze e sulla valorizzazione di queste conoscenze. Io in questo momento sono delegato dell'Ateneo, non abbiamo i proiettori tematici, il secondo abbiamo i delegati, su quella che si chiama la terza missione. E che oggi sapete, per quelli che insomma hanno la sventura di fare lo stesso lavoro, si chiama adesso valorizzazione delle conoscenze. Io credo che noi siamo in un momento, e quindi adesso entro pesantemente a gamba tesa nel tema di queste due giornate e nel tema di cui stiamo parlando. Io credo che siamo in un momento, e quindi mi affascina molto questo. Noi siamo in un momento sicuramente di early stage della ricerca su queste cose, però potrebbe essere un bellissimo momento anche insomma, di entusiasmo per la comunità scientifica locale e nazionale, perché potrebbe riportare l'Italia al centro di un movimento della pista protagonista ormai qualche decennio fa e che purtroppo ci ha visto uscire da quella che è in qualche modo la centralità su dei temi tecnologici importanti. Noi insomma è inutile che vi racconto, perché lo sappiamo tutti, quanto abbiamo fatto e quanto siamo riusciti a fare sulla codifica MPEG 4, per esempio, quanto siamo riusciti a fare sui calcolatori. Lorenzo ci è riuscito prima di giorno, e però noi dobbiamo ricordare a questi ragazzi che l'abbiamo fatto noi in Italia, il primo oggettino che andava sulle scrivanie. Poi abbiamo perso questa capacità di essere in qualche modo precursori. Io credo che questo lavoro, questa tecnologia che si sta sviluppando, questi studi che stanno facendo a Napoli, siano importanti e possono essere veramente di stimolo per tutta la comunità nazionale, con i quali evidentemente noi tutti abbiamo già dei rapporti. Io credo che questo possa essere uno di quegli esempi, quindi poi mi leggo subito alla valorizzazione delle conoscenze, uno di quegli esempi cui possiamo costruire una grande azione sistemica locale e nazionale, perché veramente l'interesse scientifico, che può sembrare estremamente di nicchia, non lo è affatto, l'interesse scientifico può essere un enabler di una serie di iniziative che, se in questo momento decidiamo di intraprenderle, ci vedranno potenzialmente. Poi è chiaro, noi facciamo un lavoro che è sempre un investimento, non noi seminiamo, poi quello che riusciamo a raccogliere il frutto di tante altre cose, voglio dire, non è che è deterministico, però ci potrebbe far trovare pronti voi tra qualche anno, e dobbiamo pure avere la capacità, e spesso noi questi universitari non abbiamo, di fare un lavoro che probabilmente e del quale non saremo noi a raccogliere i frutti, ma saranno quelli che verranno dopo di noi. E questo però credo che sia ancora più interessante, perché dà ancora più senso, diciamo, a quello che poi è il nostro lavoro, in qualche modo anche di quelli che devono segnare il campo. Perché dico questo? Qui sono a disposizione, ringrazio Francesco, ringrazio Giampiero, ma tutti i colleghi, ma non tanto per la giornata di oggi, tutto il lavoro che ci sta, tutto il lavoro scientifico che ci sta, tutto il lavoro organizzativo che ci sta. Io sono a disposizione, stiamo a disposizione come Ateneo, perché questo è il momento, per esempio, per lavorare molto sul tema della valorizzazione. Io invito tutti, giovani e meno giovani, anche ad essere un po' più coraggiosi rispetto a dei temi, per esempio, legati alla proprietà intellettuale. Cioè, cominciamo a fare dei ragionamenti su brevetti, cominciamo a fare dei ragionamenti su spin-off accademici che ci potrebbero portare, una volta che evidentemente ci deve essere, diciamo, della costanza in queste attività, e sono convinto che c'è, perché insomma ho seguito le attività, ma cerchiamo di essere un po' più coraggiosi. La ricerca è fondamentale. Senza la ricerca e senza le conoscenze non saremo in grado di poterle valorizzare queste conoscenze, ma non ci fermiamo alla ricerca, perché in questo momento riusciamo a fare questo sforzo, e lo possiamo fare solamente come sistema, ripeto ancora una volta, potremmo potenzialmente trovarci tra qualche anno, non so tra quanti anni, non faccio l'indovino, però potremmo trovarci una situazione nuovamente di prima linea su queste tecnologie. Io vengo da Bruxelles, dicevo a Francesco l'altro giorno, insieme a altri due italiani, sono seduto, diciamo, in un panel di persone che stanno valutando e stanno scrivendo le precedenti e le successive. Il tema, prima Lorenzo faceva riferimento al tema della quantificazione. È evidente, vedo colleghi del Dipartimento, che il tema non è solamente quello della computazione, c'è un tema importante che è quello di comunicazione, c'è quello importantissimo di comprendere come implementare realmente, perché i modelli e studi teorici ce ne sono tanti, ma la parte di comunicazione, e c'è tanto altro. Lo troveremo pesantemente nei documenti della Comunità Europea a breve, e vi assicuro che già tutti i progetti che sono stati presentati sinora sulle varie challenge e nelle varie flagship, indipendentemente dall'obiettivo, vedono dentro pesantemente attività che riguardano il quantum, che vanno ben oltre il tema, diciamo, del quantum resistance. Cioè, quindi c'è il tema degli algoritmi resistenti al quantum, ormai è già una roba e nei progetti in questo momento under evaluation e soprattutto in struttura è ampiamente superato, siamo già a guardare tutte. Credo che qua possiamo fare tanto e io penso che l'Ateneo diciamo, in qualche modo ha già dimostrato di poterci essere pesantemente e spero e auspico che si possa fare molto di più oltre a una ricerca che è già eccellente, non spetta al 20. Grazie ancora.
Sembra essere incelato per il sole
Oppure
però ecco anche incelato sopra una serie così ecco lasciarsi nel caso di allora anche io volevo salvare tutti quelli che sono qui, quelli che sono collegati da remoto. Io sono il direttore del centro SESMA che all'interno di Federico II, il centro servizi che si occupa dell'attività di metrologia, ma da qualche anno anche del discorso del trasferimento tecnologico. Quindi è un po' il luogo dove quando uno ha delle attività di trasferimento tecnologico, se non ha più di lui una capacità di fornire servizi a chi fa trasferimento tecnologico, il trasferimento tecnologico resta solo un'idea, non diventa una questione pratica e quindi il CESMA appunto nella sede nuova, diciamo, oramai ne parliamo sempre come sede nuova, ma in realtà oramai sono un po' di anni, 7-8 anni che è operativa, San Giovanni in qualche maniera offre la possibilità di avere questi servizi. Volevo proprio testimoniare quello che diceva anche hanno detto Lorenzo ed Antonio, cioè il discorso che l'impegno di Francesco e di Giampiero su queste attività va proprio incontro al discorso del trasferimento tecnologico in maniera molto pesante. No? Francesco, tra l'altro, è un componente storico del CESMA, è un membro del comitato direttivo da tempo e in qualche maniera su CESMA si concentrano tante iniziative di trasferimento tecnologico legato al mondo quantum. Abbiamo sicuramente il discorso del computing ed è un discorso legato proprio ad una collaborazione aziendale, quindi sostanzialmente a un laboratorio congiunto con un'azienda, ma c'è un discorso in fieri importante esteso alle communication, esteso alla capacità di fare accademy sull'attività di sviluppo software e quindi il discorso diventa ad ampio spettro. Abbiamo avuto attività e idee di progetti anche nell'ambito del quantum sensing e sono tutte attività di frontiera. Sono talmente di frontiera che in qualche maniera diciamo riescono a essere leva per un salto, perdonate la cosa, quantistico anche locale, no? Sia Giampiero che Francesco, l'avete visto anche in questi giorni, sono molto impegnati nel rapporto con loro. Posso essere testimone di questo, sono 24 ore su 24, diciamo, se eravamo nel periodo del Covid assieme, no? Cercando di mantenere vivi comunque i contatti anche in quella fase e sono molto impegnati sulla realtà locale proprio perché si cerca di avere questa esperienza, cioè non vogliamo partire con un'idea che in qualche modo bisogna attendere del tempo per arrivare a quello. In realtà il, tra virgolette, futuro è già qui e se venite a San Giovanni anche con loro, ma anche nelle altre sedi dove si stanno avendo queste iniziative, potrete toccare con mano queste attività e soprattutto potrete toccare con mano un fatto importante del quale loro si sono fatti promotori, che è quello del coinvolgimento di giovani leve molto avanzate che probabilmente sarebbero andate altrove. Questo non sarebbe stato un male di per sé stesso, ma che riescono comunque a trovare anche qui presso di noi, presso Federico II, la capacità di sviluppare attività avanzate che riguardano sistemi avanzati da poter utilizzare e quindi di lasciare comunque all'interno del contenuto dell'Ateneo, questo credo sia importante, questa loro capacità e questa loro conoscenza. Quindi è un contributo, Federico II festeggia 800 anni, no? Quest'anno, e in realtà quello che hanno dato loro è un contributo un po' a questa storia gloriosa che noi ci portiamo avanti da 800 anni, nel proiettarla verso il futuro, ma nel proiettarla verso il futuro in maniera in qualche modo virtuosa, cioè rimanere sulla frontiera della conoscenza, che però è una frontiera che in qualche modo coinvolge tutti, coinvolge le aziende, coinvolge le realtà locali, non è solo limitata all'ambito pur importante del mondo accademico. Quindi io volevo ringraziare, come ho detto, tutti voi per la partecipazione, ma volevo ringraziare soprattutto Francesco, Giampiero e tutte le persone che collaborano nelle varie sedi. Io, per esempio, ho dimenticato di nominare il laboratorio di nanomanifattura che comunque fa parte di TESMA e che è in sviluppo presso la sede di Via Claudio. Tutti questi laboratori sono un luogo dove si incontrano capacità, dove si incontrano persone, questo è importante, dove si incontrano servizi e questo è, diciamo, in qualche modo reso possibile grazie a loro, e la speranza è che questo sia ulteriormente possibile e propagato verso il futuro. Quindi grazie ancora a tutti quanti per la...
Ah, ok. Possiamo
Sì,
passare
sì, volevo scusarmi, poi non so stato all'aspetto professore per la presentazione e a rispetto anche di quello che ho detto, ovviamente il professor Vito manca, ma che ci raggiungerà, quindi interverrà nel corso della mattinata. Sì. Ok, grazie ancora a tutti. Francesco, vuoi fare gli onori di casa con il prossimo ospite, oppure lo posso introdurre io e poi magari lasciamo la parola ai prossimi chair delle prossime tavole rotonde. Grazie ancora ai nostri ospiti e chiedo magari di accomodarci di continuare a seguire dal resto del pubblico l'incontro odierno. Io proseguirei il prossimo blocco in programma, il prossimo intervento in programma. Lascio la parola al collegato a Fabrizio Copus, dirigente del Ministero dell'Università e della Ricerca, a cui saluto, che ringrazio per per essere presente anche se in questa modalità da remoto, e a cui lascio la parola. E il dottor Copus ci parlerà un po', ci farà un quadro di quello che è stato attuato nel PNRR e degli investimenti che nell'ambito del PNRR si stanno facendo nel settore del superconducting, in qualche modo anche legati a quello che riguarda il finanziamento privato. Grazie ancora, dottor Costa, vi lascio la parola.
Grazie a voi, spero mi sentiate correttamente.
Sì, la sentiamo bene, grazie.
Bene, grazie dell'invito. Mi spiace ovviamente non riuscire a essere fisicamente lì presente, ci tenevo comunque a dare un piccolo contributo in questa occasione che mi sembra particolarmente importante, perché l'evento di questi 2 giorni è in qualche modo la testimonianza della bontà di questi investimenti del PNRR, di queste così ingenti risorse messe a disposizione del sistema nazionale della ricerca e dell'innovazione, risorse che hanno l'obiettivo di consentire il conseguimento di risultati scientifici di alto livello qualitativo, di consentire al sistema della ricerca, al sistema paese, di posizionarsi su livelli competitivi molto, molto significativi e di riuscire anche a dimostrare la capacità del sistema di migliorare la propria performance anche in termini di gestione degli interventi, di organizzazione dei partenariati, di una capacità di spesa molto più veloce ed efficace di quanto sia avvenuto sinora. E la caratteristica di questi investimenti, noi oggi parliamo di qualcosa nell'ambito del centro nazionale, di uno dei 5 centri nazionali, ma il Ministero in questo momento segue 30 programmi progettuali per un volume di investimento di oltre 5 miliardi di euro e l'impegno di tutti, il nostro, il vostro, di tutto il sistema, è quello di riuscire ad arrivare a risultati scientifici importanti e a riuscire anche a spendere bene le risorse in un tempo molto, molto limitato, perché poi nessuno di noi può dimenticare che questi investimenti così importanti, solo il Centro Nazionale di cui parliamo oggi muove risorse per oltre 300 milioni di euro, sono risorse che poi debbono essere completamente e correttamente spese entro dicembre 2025. Quindi è chiaro che la sfida a cui tutti siamo chiamati è una sfida nuova per tutti, perché dobbiamo tutti essere capaci di coniugare qualità delle attività con la velocità di realizzazione, dimostrando una capacità che forse finora non c'era mai stata richiesta in questi termini, con questi obiettivi. E noi in questo momento siamo a metà del percorso, tutti questi progetti sono partiti ormai verso la fine del 2022, siamo a metà, siamo alle soglie, nei prossimi giorni faremo delle verifiche molto approfondite dello stato d'avanzamento sia tecnico sia economico-finanziario di ciascuno di questi programmi progettuali, perché adesso abbiamo di fronte un ulteriore anno e mezzo dove si deve chiudere tutto, dove si completare tutto, sia dal punto di vista delle attività che dal punto di vista economico. È un impegno gigantesco, un impegno enorme che non possiamo permetterci di fallire, perché lo state dimostrando voi, cioè l'inaugurazione di oggi dimostra l'altissimo livello scientifico di queste iniziative, l'importanza per tutto il sistema di un'operazione del genere. Il PNRR ci chiede di saper coniugare l'attività scientifica con l'attività manageriale, con l'attività gestionale, con l'attività anche amministrativa, in uno scambio, in una collaborazione continua tra mondi diversi, che è la chiave fondamentale della riuscita di operazioni così consistenti e così impegnative. Noi siamo al fianco di ciascuno di questi progetti, a volte anche in modo un po' severo, se vogliamo, ma insomma siamo tutti chiamati a non sollevare il piede dall'acceleratore, avendo la capacità di guidare questa macchina con raziocinio e con equilibrio. I risultati fino adesso sono molto incoraggianti, in particolare i risultati del centro di cui ci stiamo occupando in questo momento. Mi auguro che con la collaborazione di tutti, con lo spirito di sacrificio che tutti stanno dimostrando, che hanno dimostrato fino adesso, riusciamo a continuare su questa strada e, se possibile, anche migliorare la nostra capacità di performance, perché c'è sempre margine per essere più bravi. Io vi ringrazio, mi complimento con tutti, rimango collegato ancora qualche minuto e spero di vedervi presto un po' più da vicino. Grazie a tutti.
Grazie mille per il non chiedo che ci sono domande, anche perché immagino che poi la bloccheremo per tutta la giornata di oggi, di domani e forse tutta la settimana, per le potrebbero farle. Io passerei alla prossimo diciamo, blocco di incontri alla tavola rotonda, chiederei cortesemente di salire sul palco Saverio Pascaccio, che è il professor Pascaccio, grazie mille, a cui lascerò al prototipo di moderare i prossimi incontri. Grazie. Chiederei anche agli altri relatori, ufficio di riparto, Tommaso Calacco, prego, direttore dell'Istituto Complex e Quantum Systems per Center for Integrated Quantum Science, questo non c'è. Simone Montangero, Università di Padova, coach del Scope 10 del Centro Nazionale XC, e Francesco Cataliotti, prego, professor Cataliotti, Istituto CNR Reno, coordinatore SPOC 3 e NQSI. Ok. Siamo un po' di diciamo se c'era
allora, buongiorno a tutti. Io credo, pensavamo di passare all'inglese, quindi a mio senso. Va bene così, va bene, ok, pensavamo di passare all'inglese, so we switch to English, and let me introduce again the three speakers today. There is Tommaso Calacco, I presume that all of you know him, and he's the coordinator of the Quantum National Board of MOOCs in Unina, the two main institutes that are involved in the Quantum Computation Initiative, and he's a professor at the University of Bologna. Simone Montangero is the director of the Quantum Computing Simulation Center of the University of Padova, and he's also the co-leader of the SPOC 1-2 of the National Center, what we call Centro Nazionale. Francesco Saverio Cataliotti is the director of CNR INO, which is a national institute of CNR, and he's the coordinator of SPOC 3 of NQSDI. NQSDI is this acronym So let us start. Do you have a preferred order? Okay, shall we start with Tommaso?
Okay, we can start. Yes.
So the other two is going to be different before.
Okay, can I use the mic?
Of course you can. You have to speak close to
So, and can I have, no, it doesn't work. Does it work? Yes, it does work. So can I have, is there also a pointer or something? This one. Oh, wonderful. This one is the pointer. Previous. Oh, wonderful. So on switching on is wonderful. So, and maybe we will no, so yes, I can still switch on. And is there a way to have the slides on the screen? That will be very helpful. Thank you. So, okay, so it's fantastic to be here. Okay, so here you see, very good, perfect. Just give me a second.
Yes, yes, no. Yes, it's loading. Fantastic. Okay, so, well, thanks a lot. It's fantastic to be here. No, they say no. Okay, I will say some words to waste some of your time. So, well, it's a wonderful pleasure to be here. It's actually amazing. You know, I am meeting several people who I met more than a quarter century ago. Okay, when this whole thing was not yet called quantum information, quantum technologies, or anything, and we have now this amazing progress that actually, you know, Italy has. I also have a position in Germany. So Italy at the moment has a factor. Wow. Now this
this is the Germans, which are kind of because I was going to say that Italy now has a fatter computer than Germany. No. So I can whatever. I can speak like that. Do you prefer this? I can do that. Is it fine? Very good. No, no, oh, very, very good. Oh, okay. So it's complex quantum systems. So as I said, Italy and Naples now has a much fatter quantum computer than any quantum computer in a public organization made by a public research institution in Germany. So this is why the Germans now try to sabotage this conversation. Yes? But this is a fantastic thing, of which of course all the Germans are also going to be very happy, because this is really a European undertaking. And so what I'm going to say is that this shows here that we have a foundation for a whole European ecosystem. And I'm going to say a few things about how we are shaping that. And this, of course, in case the pointer works, which is of course not to be taken for granted, and actually is not the case. So I will push the button.
Franco, mi senti? Siamo solo noi. Siamo solo noi nella riunione, cioè non ci sta, siamo solo noi, siamo io e te. Quindi, che ne sai, cioè, tu hai seguito, può essere che è finita, che l'hanno chiusa, io che ne so, che sta riunione, team e Kist, sono trasuto come canale 1, tu stai dentro come canale 2, stiamo...
So I'm not saying this in order to, I'm just trying to convey a message. Things are going so fast that even for someone like me who's, following this very closely, it is difficult to understand what's going on. Every time I listen to Tommaso, I learn something new in this respect. Thank you very much for making this possible. Francesco and Giampiero, in one of the slides that Tommaso showed, I wrote it down because I didn't want to forget. 25 superconducting qubits with 99% 2-qubit gate fidelity. Do you understand the reach of this challenge? I'm sure you do. 99% gate fidelity on superconducting qubit. It's amazing. I mean, a few years ago, I wouldn't even dream of this. Which time point do you have in mind?
Well, I would say that we are close to getting that in a couple of European projects with a dozen qubits. At the moment, the 99% fidelity was actually demonstrated preliminarily by Rami Barents in Jülich 2 weeks ago. The scaling to 25 is kind of within reach of the, I guess, next 1.5 years.
Okay, in 1.5 years, you're going to do that. Francesco Giampiero. Okay, thank you very much for that once again. We'll start the questions. I think we can on stage. I introduced it before. Let's leave some time for questions because I'm sure there is going to be some questions.
Okay. So good morning, everybody. I think I need my presentations. Can you hear me? Yes.
This one, right? 24 minutes. Okay. Just give me a second. Just give me 1 second.
Okay. Good. So from the European landscape, let's move now to the national one. And here I'm this morning I'm presenting the quantum bespoke 10 the quantum spoke that I created together with Paolo Cremonesi of Politecnico di Milano of a national center for HPC, big data and quantum computing funded by the Recovery Fund. This is something that you don't see. Okay, so twice. So you have seen this yesterday. So now the National Center encompasses all Italy with many different institutional and research centers, and it's mainly focused on the application of classical supercomputing. But we have two special verticals, two special spokes, one dedicated to developing the new classical supercomputing technology, and one that is developed, that is devoted to develop the national infrastructure of the Italian environment, both at the level of applications, of academy, research centers, and industry. So here you can see the institutions that directly participated from the very beginning to the spoke. As you can see, most of them are academies. We have our national supercomputing center, CNR, and some research center on some dedicated topics, as for example, astrophysics, to explore application of quantum computing in different domains. And of course, we have some of the most important industries in Italy, and more have joined after the initial starting. And actually, this is the spoke of the National Center where industries have most shown interest to participate, to explore the potential of this new disruptive technology, and to be prepared for the challenges in the coming years. So what are our focuses? Well, essentially, it's the whole stack of future quantum computing and its integration with classical supercomputers like the Leonardo machine in Bologna. So we go from the physical hardware, and we are here, of course, for that. And then we go up to different level of abstraction. So the development of firmware, so the whole software that is needed to make this machine working, up and running. And to reach 99% fidelity of gates in a couple of years, hopefully. Compilations, and then we moved on the more abstract hardware agnostic level, so emulations of these machines at the level of quantum circuits, algorithms, developing of new ones, and exploring their applications of standard and new ones to different applications in different domains at the academic research level, but also at the industrial levels. So to achieve these goals, the activities are divided in three main work packages, which again follow the same structure. So we go from hardware and firmware, and then mapping, compilation, and quantum computing emulation, so an intermediate level of abstraction, and then the upper layer with software and applications. And here you can see all the participant activities. So what we strongly wanted while we were shaping this the activity of the spoke was, these two levels were essentially kind of natural, but then at some point we had to face the challenge that somehow the Italian landscape in terms of is this better now? Can you hear me now? Yes. Okay, fine. Great. So we had to face the challenge that Italy was kind of little behind with respect to the European landscape in terms of developing the hardware of quantum computers. And so what we did was to take the challenge, and actually we convinced the governments to make a huge effort to invest additional 20 million euros in 4 labs with the goals of developing the 4 main hardware platforms that we have already seen before, so superconducting circuits, and this is why we're here today. So I'm very, very happy because this is somehow the demonstration that that what we did was a good choice. But then we also developed, we also funded a lab, a lab in Florence, which is going to build the neutral atoms quantum computer, the lab in Rome on photonic circuits, and a new lab in Padua on trapped ions, in such a way that we can put Italy enable Italy to compete in the environment, in the global environment of this global challenge, independently from which technological platforms will take a lead, and most probably, as we will see, that all of them will be developed in the next year. We are able now to participate to the European landscape and of a quantum computing industry. This is the hardware. Of course, we want also to make our industrial landscape to be able to compete on the challenges that are coming. So most of them in the application domain are related to complex optimization problems that are the kind of problems for which most of industrial challenges can be recasted at. So now we are with different partners of the spoke. We are exploring applications of quantum computing in different domains, like in Earth observation, in traffic, and logistic in general, portfolio optimizations, but also machine learning and chemistry and molecules and more. So let me spend a couple of minutes just to go a little bit, given this is supposed to be also a scientific talk. So I will list some of these projects that are ongoing, and in particular those related to work package 1, so algorithm applications. We will hear much more details this afternoon in the dedicated sessions. But you see, we have many partners that are exploring the potential of quantum machine learning and apply them in many different domains. We have practical applications on science related of quantum computing in science related basic related problems, and leveraging on the strong tradition of Italian landscape in high energy physics, for example. So for particle tracing in experiments at CERN, or image classifications in different domains, again going from scientific experiments to medical applications, and also is optimization, bias-spide optimization. We go on quantum simulations and modeling, yet another pivotal applications of quantum computing, of course. So we have projects exploring quantum simulation of quantum electrodynamics, quantum thermodynamics, so complex many-body quantum system, that the capability of simulating efficiently them will enable a lot of developments in basic science and again in industry. And finally, some hybrid quantum classical system applications. So essentially studying how we can hybridize and performing computations that will be made partly on classical supercomputers and accelerated in parts on quantum processing units. This is, the idea is clear. We know that this will happen, but the whole technology and the whole knowledge to be able to enable this process efficiently has to be still developed in its main parts. So there is a lot of work to be done. Okay, so let's move on. So this was the highest, more abstract layer. Then let's go towards the hardware, the machine, and here mostly the activity have been developed have been developing the quantum emulation. So in this period where quantum computers are still very, very small and noisy, we want to have to be able to explore their capability at most, and to do that, we have been developing together with Cineca a high-performance computing emulator of a circuit-based quantum computation. So this is based on tensor network methods, powerful classical numerical methods that run on supercomputers that mimics a quantum computer. Okay. And now the idea is to try to see how far you can push this, and this is based on our ability of compressing quantum correlation or compressing entanglement present during your quantum computation. If you don't generate enough entanglement, your quantum computer is useless, because we can emulate these with hundreds, thousands of qubits. So your quantum computation has to be efficient and has to generate a lot of entanglement to be really, a quantum computation. So here, for example, you see an emulation of a quantum Fourier transform, one of the most important and efficient quantum subroutine that we know, that has been developed up to 300 qubits. So you see a pretty large quantum computation, well beyond what we can do now. This can be now emulated on our supercomputers. And this, of course, enables a lot of investigation, preliminary investigation, optimization on a lot of software that will be then eventually necessary to run on real hardware in a few years to come. So one of the main results of this is, so you can, this quantum T libraries that we developed at Padova, and that now together with Cineca is available for everybody as a module of Cineca. You log in with your account, load quantum, and you can send your Qiskit program or a couple of other interfaces and see if you can run it and how far you can go with your preferred quantum computation. Alongwise, we have been using similar tools to develop a large-scale digital twin of a quantum computer. In this case, this was a fully fledged emulation of a 64 Rydberg-Atom quantum computers with qubits. So these are 64 free-level systems with noise, with cross talk and everything you can think of, and this is of course something that is very, very useful to really model what's happening in the machine, finding the bottlenecks, seeing where to improve it, and so on. And so this is again available. We would be very happy to so this is flexible, so we can apply it to the supercomputing technologies, trapped ions or whatever. And then, of course, we have quantum benchmarks. Politecnico Milano is working on an infrastructure, and here we will hear more this afternoon from Paolo to have a tool, a standard tool to perform benchmarks on futures algorithm, as long as following the development of the hardware and of our capabilities. Okay, so that's all for work package 2. Then we move now from work package 3. Firmware and hardware, and here, okay, I'm simply go fast because we have already heard a lot, but mainly we have our the very first exciting results on superconducting and photonic systems. So superconducting, you already know everything, but also in Rome we have a very fast development of photonic circuits for quantum computing. Okay, so, and this is kind of the summary of the key result up to now. So we have, which is what we can, very exciting. I think we can declare this to be a success, because everything is going well beyond the planned goals. I have also to mention that, this was a kind of initial activity, but we also have started many projects with industries. So there were dedicated funding to start industry academia projects. So it both started a few months ago, but there was some time required to open up calls and close them and so on. But now they are up and running, and I'm sure that in some months from now, I will be able to also present very exciting applied results with industry. You see, so we had 8 projects. There are all these partners involved that enthusiastically all of them proposed applications of quantum computers in very specific domains. I have to say I was really surprised in the capability of our industries in Italy already to be ready and start very focused on very applied projects that are giving already very nice results. So I would say that also the goal of getting our industrial landscape to move on and get even more ready for the quantum revolution is happening. And this is kind of a list of the titles of the approved projects. So you see that they cover many different domains. And moreover, a couple of months ago, we also closed additional calls for new members or people external to the spoke to participate to these efforts, and so even more academic institutions and research centers and industry are now participating in this global effort towards the development of our quantum computing capabilities. And with that, I thank you for your attention.
If you moment, I think we postponed the question. Can you go back 10 slides? Sai dove hai 2 grafici, quello rosso e quello nero, ti facevo notare, quello dove c'hai la performance classica e satura.
Questa qua? Sì.
Ok, grazie. Okay, for the young people in the audience, in essence, this is an extremely beautiful and concise, thank you very much. So this is how why quantum computing is important in a nutshell. If you are able to put a few more qubits, n is the number of qubits. The red curve is the quantum performance. This can be taken as an index of performance, the time or something. So you see, the blue curve is saturating, it's linear. The red curve saturates when the computation becomes classical. So if you are able to perform one qubit more, the simulation becomes much more performing. That's in essence what you should understand. Sorry, I know I'm simplifying a bit too much.
Okay.
Okay, you see, that's what quantum computing is mostly about. Thank you. Simone, I know I'm simplifying a bit too much.
No, I would simply say that you see that if you don't generate enough entanglement, the quantum computation is polynomial on the classical computer if you do it properly.
Yes.
So only some quantum computation are really quantum, or we need a quantum computer to do that. Those that are not present here because we cannot do it unless, So this is essentially, this is the exponential. So this is Qiskit is doing this exactly. This is the exponential thing, and then it goes on with the tensor network. So,
yes.
Okay.
Thank you, Francesco. You're the next speaker. Thank you very much. Thank you again.
Dovrebbe esserci una presentazione.
Sì.
Mi sentite? Che and just going on quello in Cina. Sì. Non sembra un nodo show. Sì. So, thank you very much. Thank you very much. since I reorganized slightly this presentation since I could not unfortunately be here yesterday, so I introduced a few general slides on the National Quantum Science and Technology Institute, which is one of the initiatives within the Italian recovery plan. This is the landscape that emerges from the recovery plan for what I believe is, and it should be considered, the ramp-up phase of the Italian effort on quantum technologies. It's something that is funded for 3 years within the recovery plan with 200 million euros, and it includes, as Simone was mentioning, the quantum spoke within the National Center for High Performance Computing, the development of the European quantum communication infrastructure, a new infrastructure for research, and the partnership that I'm going to describe within the National Quantum Science and Technology Institute. And this is completed nowadays with what is going to become the heart of the effort to systematize this into a strategic direction, as Tommaso was mentioning, with the ministries and the community. And this is given by SISTEC, who is going to be the community forum to give us inputs. This is the landscape, and I repeat, this is the ramp-up. Those 200 million euros are the ramp-up. We have to go in the fully fledged, as yesterday we have been listening to our ministry representatives, is the time to get a strategic direction on it, and Tommaso is going to help us on that, as he was mentioning this morning. And we are going to follow within Europe and keep Italy rightly at the forefront where it should be. Now, what is NQSTI? NQSTI is an initiative which goes at the bottom, in the sense it goes at the lower TRL levels for quantum technologies, comprising quantum research, the education and outreach, supporting international program, and going to feed into companies what is coming out of research institutes and institutions. As a matter of fact, the first international program we have been starting to fund is Quantera. We have provided the funding for Quantera 2, and we are now working together with the ministry and the other initiatives to fund Quantera 3. This is, in a nutshell, what we are going to do, what we want to do, and what we should support. And this is what, let's say, a bit of numbers. A bit of numbers is the technology readiness level, as I said, is the bottom ones. These are the institutions where the technology is developed via research. There are quite a lot of researchers, but not enough. I should show you something afterwards. This is the funding, but this funding includes 23 million euros that are going outside this partnership of 20 institutions. And we are going to hire or are hiring these new researchers. I hope this is actually, I'm sure, not I hope because I know the results. This is the last time I show this empty picture. This is the beginning of the initiative. We are completing this thanks to this open course. We could not fit all the community. We heard yesterday the director of the department, the mayor. The mayor is not only the mayor, he was the minister of research when this started. They have told us this is a collaborative effort. We will go to strategic directions. We need to get all the community on board. Italy is a diffused community. This number, which was given by the competition text, was too small. We are now completing this, and this picture, which has empty spots all over Italy, will be completed. We will put in all the people that have to be. And now we are ready for the new strategy that we are going to develop. The structure is such as to support technology. So we didn't go for the verticals of the flagship, but we went for the platforms. So we have the theory that is going to support the decision, not only the decisions, but the directions for research, the platforms for the devices, atom-based, photon-based, electron-based. We are not talking of quantum computing here. We are talking about all kinds of technologies. So not a single vertical, but all the verticals. These are going to be electron-based, means both semiconductors and especially superconductors. Spoke 6 is, this is language of PNRR, but you're all used to it, so I don't have to explain what it is dedicated to the integration and to the complete systems. But all these has to be accompanied by the connection to the industries on one side and the production, and on the other to the knowledge makers and to the development of new skills and new abilities within the field. Basically, I fortunately see this is an academic institution, a lot of young people having new people on board. Without you, we are not going to do anything. It's your thing, this part. Not only this part, but what grows out of it. These are the spoke leaders, just to give names to the people. And these are the spokes, as I told you, that are considered to do, that are tasked to do the different things. I'm going to delve now into the atom-based one, which is the one I'm responsible for. So this was just to give you an overview. Last but not least, what we have been doing in this year. Basically, we exist since the end of 2022. So 23 is our first year. We have already hired 87 new researchers who are producing a lot. We have already more than 200 publications. We are distributing the 23 million. We have published 7 calls, basically for roughly 19 millions, actually, here. And we have financed Pantera 2. So this is proceeding. It's proceeding quite well. I have not put an important thing here, but this is because we are going to discuss with Dr. Kovic tomorrow what we are buying. A lot of this stuff is buying equipment. As he mentioned, buying has to be completed by next year. This is the foundation of the future for quantum technologies in Italy. Not only us, but the center and all the recovery plan. What has been done here is fantastic. You can see it's the image of what we could do with those money, what we can do with that money. It's something that goes on. We spend money, but it will go on. Okay, we spend the money in 2 years, but it's the future of our research for the next 20 years. Now, these are connections that have been created between the 20 partners, and we are hoping to enlarge this circle, not change the topology. We completed the milestone for the first year. I go fast about this. These are milestones connected to the activities of the different spokes. And now I go into the atoms. Again, I'm not going to go too much in detail. As Saverio is mentioning, we have to leave time for questions. So I'm not going to go too much in details, just give you a flavor of what it is. Atoms is mostly centered around the Florence area and the Tuscan area, because that is where that is localized in Italy. We have partners from the National Research Council, the University of Florence, INFN, Trieste, where there is a new and important exciting developments, together with CISA as a theory support. And I would stress very much the presence of Leonardo here. We have also an important company. We heard yesterday from Massimiliano, the strategy of Leonardo to support quantum technologies is fundamental. That on the technology pillars, we have on board our friends from companies. These are the activities, and you see Leonardo is involved in many of them, and in particular in that about sensors. You know, atomic interferometers are important sensors. These activities are developed by the different partners. Again, I like to put a few names here that you might recognize of the people that are working on it. Just for gender, some of these are, and as correctly is, there is a good distribution of men and women. I'm not pointing that out, it's natural. That is the natural evolution of this field. And it's a fantastic situation that we actually can keep up with that. Now, the number of researchers in this book is roughly 1/10 of the entire center. We tried to hire all the 8 new researchers, but we could only hire 5. This is something that we have to improve. We have to go to, sorry to use this word, it's not the right one. We have to train more people for these technologies, and we have to recognize what are the new skills that we need to get on board. And this is mainly an experimental effort, so the papers in 1 year are a very small number if you compare with our principal theory, but it's a significant one. And being a significant one, I point out that the last 2 highlights that came out basically this month. This is connected to our friends in the superfluid version of the Josephson junction. So this is a neutral Josephson junction connecting a naturally occurring supersolid phenomenon. So the supersolid locations are connected by weak links, and as Antonio Barone taught us, me included, when you have a weak link between condensates between these things, you have Josephson effect. And this is instead another exciting development that we have actually in the lab downstairs at Lens. This is in Pisa, this is in Florence. Here is, we are able to paint basically circles, rings, onto a system, generate quantum gas, and then you observe a lot of instabilities. But the main message here is that you can actually paint any potential you want and analyze the what is happening both in situ and in expansion. These are expansion pictures. Just to give you a flavor, this is the phase and this of the wave function, and this is the real part. Okay, so it's you can get a complete information about and visualize the wave function. This is one simulation to consider this as a vertical, but it could evolve if miniaturized also to sensing, because of course the angular geometries can identify rotations and different kind of things. So I am very glad that I can actually conclude on something scientific. I try to give you a flavor of what's happening and why we have this initiative here. It's fully integrated in the European strategy, and it's going to be even more integrated with these initiatives of the Ministry of the University and the Ministry of Industry. And with this, I thank you for your attention.
May I ask the 3 speakers to come back on stage, and maybe we get a few questions from the audience. Okay. Thank you. Our next question from the audience. Whatever. Francesco, you asked, you rompi il ghiaccio. You know, it's
Hold it.
Okay, absolutely. Okay, Tommaso, last night you mentioned something very interesting. National strategies from Europe to Italy. So, which are the plans? I think that's important for clarifying.
So the plans that exist at the moment are the strategic research and innovation agenda of the quantum flagship, which we have updated just a few months ago with the participation of a lot of Italian people. Then there are already many documents, and Francesco has done an enormous amount of work actually in putting together, you know, even before the resilience and recovery plan, you know, really, you know, the Italian strategy in the PNR with 1 R,
the Programma Nazionale della Ricerca, so there are several acronyms. And and there are, of course, the different strategies and plans of the National Center, of the partnership, of the other infrastructure on photonics and quantum science, which is IFOX. And this is what exists. Now, the plan for the future national quantum strategy, all we know is that the ministries, because I learned this last Friday, so I was actually in Berlin with my bike. I had to leave my bike in Berlin, hop on a taxi. While I was on the taxi, I booked a flight, and then I had to go to Rome because they had this meeting in which they said, now we want really to do something together. And so the plan there is in the next several months, so over the course of the summer, to put together all that we have, all the knowledge, so certainly not restarting from scratch, but bringing together all the wisdom that has been collected at national and European level, to also look in a systematic way about all the activities which take place in this country, both on the science and on the enterprise side. So this is where also the Minister for Enterprise is involved. And then to create a draft of what are the areas where we are strong, where are the areas in which we can improve, and perhaps what are the areas where we really are not active and we should just, just leave out. So to really have a plan that could be the basis for even a strong, legislative intervention. Actually, even last week, but this was from an opposition party. They have had a press conference in which they have announced a proposal for a law on quantum technologies, not from a government party. And I find it very interesting that now the government is saying essentially the same. And we will know around the fall how concrete this can become. But I do see as a very promising aspect that this wish, as we see in other countries, actually the Quantum Information Act in the US was the only bipartisan law which passed under Trump, okay? And we see this in many other countries that for some good reason, I suppose, so this is a topic which finds support, across the political spectrum. So I'm optimistic that this time it might really happen. And the Quantum Pact that we have at European level, which Italy was among the first to ratify, is a very big push in this direction, because now, not only if you do a national strategy which is aligned with Europe, is not only you are doing it for yourself, but this gives you leverage to intercept also these CHIPS funds. For instance, the CHIPS Act funds come from Europe, but they require also funding from Italian level, from national level. And this is a discussion we had yesterday in the cabinet of the Minister for Science. How do we organize that? So the final answer is there is at the moment no plan, and there is an agreement such that the plan will have to emerge from input and validation from the community, both scientific and industry. And this is a fantastic thing, because not in all countries of the European Union, this is how it works. It works like this at European level, that the European Commission, the decision makers, they want to listen from us. They really take what we produce and they use it as an orientation for their calls. In other countries of the European Union, this is not the case. Sometimes the governments are doing that in a decoupled way from the scientific community. And here, instead, this is how they want to do it. And this is why they asked this Italian society, SISTEC, to be strongly involved through the President Massimo Palma, who is also here today, and will be the voice of, here is Massimo, will be the voice of the whole community there. And then Francesco is involved for the national partnership, and Antonio Zoccoli, the president of the Foundation for the National Center, is involved. So I mean, we agreed that the process will be like each of us will be a funnel towards each part of the community to intercept everything. So the plan is not yet there. We are going to do it together. And it seems that the government really wants to listen, because they are actually asking us to do that. Okay, so it is a very special situation, which I think would even be a role model for other European countries, as a matter of fact.
Thank you.
Another question.
Please. A short one.
Short one. No, Francesco finished with the great result, and I know that Simone has a great result too. And is it the time to announce or not?
C'è ancora le barre.
Next
It
week.
is a secret.
It's an embargo. No. Stay tuned. Thanks.
There is another question.
This is probably it's going to be a naive question for someone who was very interested about quantum computing. Can you give an example of something that we do today on classical computer that can be done better in quantum computers? Also, an example of something that cannot be done better. Yes, that to use classical computers.
Yes, certainly. Okay, the answer depends on how you define do better. Okay, so that's where you have to start. So if you are happy with polynomial speedups, then you can go to Quantum Algorithm Zoo website and you will find a number of proofs in many different problems in linear algebra, solution of many different things, where you can actually show that there are polynomial speedups. If you want to have a proven exponential speed up, meaning that you know a problem that is not in P but is in BQP, algorithmic complexity classes, then we have a formal proof on a problem which is called the correlation, which unfortunately is useless. But if you are theoretical guy, you are happy with that. You know that proves that the two computational approach are really different. And then in between there are a lot of heuristics, okay, where we know that we can get some speed up. For example, you know in complex optimizations, those that I was mentioning before. So even NPR problems, so they are NPRs, but a lot of the job of industries, of many industries, is actually to solve them, despite they are NPR. There we know that we will get some speed up using quantum computers or some improvements. And this again depends on what, and typically there are three. The first immediate improvement is speed up, which actually you might realize that is not actually the most interesting one at some point. So it might be speed up, but it's not the most interesting. The other interesting improvement might be the quality of the solution. So I might take the same time as for the classical one, but I give you a better solution. So you are happy to give 3% of 5 billion euros, which is a lot of money. And then the third one is related to energy consumption. That is, it might find, eventually you might have a lot of instances for which the quantum result is, similar to the classical one in terms of quality and in terms of speed up, but in one case you have used a supercomputer that consumes like a small city, and in the other case you have used a quantum computer that consumes as a single house, a boiler, a heat. So yeah, we know that this will come. I hope I give you an overview. Then it's a long story.
I think Tommaso, you wanted to add something.
So I don't know, are you a computer scientist, a mathematician?
Well, I do illustrations, molecular dynamics.
Okay, good, fine. So the simple answer is molecular simulations, like predicting properties of chemicals and of materials is something that is proven to be exponentially faster than a classical machine, because it's a quantum machine. This was the original idea of Feynman. So simple answer. And something which you do not do better is, of course, like word processing. Okay, a lot of the things, most of the things that you do with computers today, you are not going to do better with a quantum computer. There is no point in that. And something which you might be able to do better is all of AI. provided that there is a sufficient technological base in terms of memories and so on, and efficient algorithms for optimization, because AI is optimization. So this is sort of a more sort of low-level answer than the very sophisticated answer that Simone gave.
Let's get another question. If there are no further questions, then let's thank the speaker again. Thank you very much.
But I think actually the occasion I was leaving space for questions, but to finish the answer on the question before, we go on creating strategies, fantastic roadmaps, and eventually taking even strategic decisions on funding. But remember that this is an innovation process, which is done by people. We have new fantastic tools. People will use those new fantastic tools to have new fantastic ideas. So it's not necessarily that we have the answer. Actually, it's exactly the contrary. We do not have the answers for many of the questions. Somebody will find a new fantastic answer, and this we are certain. Okay, that is the name of the business.
Thank you. I would like to thank the speakers for conveying. Maybe start with this message.
Certo, allora sì, allora diciamo il download di questo qui, prima di passare all'ultima tavola rotonda della mattina, la Fabio Milone che ci ha raggiunto finalmente. Prego, a lei. Come preferisce? English. Vogliamo continuare?
As you prefer. Greetings in general in Italian, but if you...
First of all, I would like to apologize for being late. I was involved in another event somewhere else in the city, so really apologies for that. I'm really glad to be here, and I just wanted to stress one simple concept. I am the director of the Department of Electrical Engineering and Information Technologies. And the thing that I want to say is that I'm very proud to be here because I really think that any, say, challenging scientific endeavor like that we are discussing today needs say, different competencies to be brought up. And quantum technologies is one of these examples where the contribution of both physics and engineering is fundamental. From time to time, we listen in mass media and public opinions that university tends to build barriers between different topics and so on. So scientific sector, so on. This is nonsense, of course, from scientific point of view. And in fact, we are demonstrating this because here at we are putting together a team which is in fact encompassing different competencies, and this is the only way in which we can go for a great result like that we are pursuing now. So really thank you for this opportunity and good luck to all of us. Thank you.
Allora, I just want to continue in English. Okay, I ask you, okay, to reach us the next chair. One moment, I take the phone. Please do. Sorry. Okay. Okay. So sorry, we can continue. I ask to reach me on the desk the next speaker. So please welcome to Giovanni Miano.
Yes.
Morning. Alessandro Bruno. Yeah. Okay. Thank you. Stefano Poletto.
Yeah. Yes.
Marco Arzeo. Okay. Welcome. And Davide Massarossi. Okay. Benissimo.
E Massimiliano Spezia.
Oh, sì, no, Massimiliano Spezia.
Good morning. We start the section. The main topics of this section are relevant to the open challenges in the development of superconducting quantum hardware for quantum computing. The speakers have been already we start with Alessandro Unina, co-founder and chief technology officer of Quantum. Please.
Thank you very much. Does this work, please? Yes. Thank you for the opportunity and for this splendid occasion that we have here in Napoli. As I mentioned yesterday, I am myself Napolitan and proudly a student of the Federico II, and it's a great pleasure to see here a lot of old colleagues. I migrated about 13 years ago to go to the Netherlands. I was looking for my first postdoc, and I think I settled there for good, finding there a thriving ecosystem that I will try to describe a little bit in the slides. Nevertheless, I will give also a very brief introduction to how Quantwerk came to be and what is mission and goal. I will introduce our products and I will go a little bit more into the detail about what you can actually do with this quantum processor that has been installed here in Napoli. And then a few words about the importance of having an open quantum approach where components are developed by specialized players and then they need together to make a powerful computer. So as I spent several years in the group of Leo Di Carlo at QTech, I've been exposed to a lot of frontier quantum physics over the year. We performed the very first NISQ era algorithms, so small demonstrators of EQE or QAOA. Those are analog and digital simulation of small problems or optimization problems. We've been heavily involved in logical qubits or error correction operation, and later I'll show a little bit what building block and important steps can be done also here in Napoli. Always an emphasis on the quality of quantum components such as resonator and qubits, because as we will see, in order to really get into the so-called quantum advantage, one needs not only very good qubits, but I mean a lot of qubits, and that's where the mission of Quantwerk comes into. Over the year, we also put together the very first online quantum computer in Europe, the so-called Quantum Inspire, that has been recently upgraded and it's open to anyone. So Quantwerk was founded 3 years ago. It's quite a journey to step out of the academia and becoming an entrepreneur and a great team. That's definitely lesson number one for younger entrepreneur with a good idea. The team is essential. It's not a single man endeavor, and having partners with complementary skills is probably the most important aspect of success. We also have good scientific advisors and angel investor, Professor Rami Barnes, was mentioned a few talks ago. He was one of the first to recognize our potential. He invested himself and continuously challenging us to where we are and and how we do it. So we founded Quantware because we recognize that there is a quite mature value chain around quantum technologies. Nowadays, it's pretty easy to order a fridge or select which control hardware vendor you want to use for your system, or which software also to put on top of that to run your experiments. But a few years ago, there was a clear missing part of the stack. The quantum processor were not available in an easy way on a commercial basis. Typically, you require large foundries. We heard yesterday from Brighetti, and we know how also bigger players are well positioned for it, but most likely they produce processors for their own use. And if they want to sell something, it's actually a monolithic system, something that it's a closed box where you have a very high level interface above the stack, but you have little access to the actual components, little room to change them or to study or to do actual research and innovation on the lower part of the stack. And that's where we decided to actually open the market of quantum hardware. I think we were probably the first one to offer quantum processor on the market, and also quite soon one of the few to offer quantum amplifiers. And after 3 years, we are doing great. We've been providing quantum processor on more than 18 countries, distributed over 4 continents. And our key differentiator is that we have an extremely short lead times, especially for standard processors, where we have them on stock characterized. We do pre-characterization of every single component, so we have excellent specifications to begin with. And because we mass produce them, we can have quite a lower cost compared to the other alternatives on the market. Over the years, we started with very small devices for 5-qubit QQ, called named Soprano. We quickly moved to a larger QQ, the 25-qubit QQ Contralto, on which we will spend quite some time in the talk. We started in 2022 with what we called at that time fabrication as a service, so small foundry services in view of strengthening key collaborations with partners that perhaps don't have access to a foundry but has interesting designs or are developing new kind of superconducting based qubits that are not the standard transmon on which we base on the QQ, but more like fluxonium or flux qubits or half qubits and so on and so forth. As I mentioned, we introduced the Traveling Wave Parametric Amplifier, which is a key component for a high fidelity readout chain. And all over this time, what we were really developing behind the curtain was a scalable architecture, what we call Tenor, which is the first time that a QQ is not connected laterally. I have a couple of slides, but actually all the input-output goes perpendicular to the qubit plane, and that's what we believe the truly scalable architecture that at the same time will enable for better qubits, because the material science to have always lower TLSs and higher coherence time. It's always ongoing, but at the same time unlocking more qubits, avoiding bottleneck and crosstalk of lines. The grand goal, of course, is to get to at least in the next 2 years to 1,000 qubits. And we see that as an important milestone where predictions are that so-called utility scale application will emerge. So around 1,000 qubit with current coherence is where the inflection point is expected. Is the moment in time where we will be able to do computation that is beyond what is classically computable with the current supercomputers. So a few words on the parametric amplifier, which is an essential element of the readout chain. If that's the input feed line coupled to a few qubits, like 5 in this case, this level signal has to be routed via an isolator and directional coupler into this parametric amplifier, which is actually the best amplifier that nature gives us. Is quantum limited, adds just the half photon of noise per hertz, which is what's set by the Heidelberg limit, and has quite outstanding performance. Has a amplification bandwidth of above 20 dB for more than 2 gigahertz, if you think about also the presence of upper band, and has typical compression point of 100 dBm, means that it can be used for multiplexing readout of around 7 or maximum 8 resonator concurrently. So this is also customizable for customers that are interested in different experiments. There are people interested even in lower frequency than 4 gigahertz, or customer dealing with dark matter research that are interested in even higher than 12 gigahertz bandwidth. So we are able to tune the resonant element in fab and deliver devices that are customized. And also, as I mentioned, every device is already pre-characterized in-house, so to have basically a very easy tune-up procedure and reference map of where to find the ideal pump settings for best performances. Now switching to the QPU, we spend a little bit of time to the current installed QPU here in Napoli. And don't forget that a 40 qubit QPU is already coming before the end of the year. So that's a layout of a contralto, 25 qubits. Don't really know why this conference is 24, but on the QPU there are actually 25 qubits. Let's go through the elements that compose such a device. At the periphery, all these are microwave launchers connected to wires that extend outward, and microwaves are then able to travel along these lines that are coplanar waveguide resonators. If you notice, there are 4 of this symmetric, so you can think of this as a multi-core processor. Basically, there are 4 independent cores where then each qubits that are this object here is able to communicate with its nearest neighbor. So this enables already for a parallelization, if you want, where you can decide to operate these 4 cores at unison, but also you can decide to use them in a separate fashion, focus on local interaction and running perhaps multiple experiments. If you notice, there are also 4 qubits at this corner that are not part of this grid. These are typically used for benchmarking and to do experiments such as single qubit calibration or perhaps interesting tests where a user wants to verify what component of noise is coming from flux noise rather than other noise. And that's perhaps an easy experiment where, because all the qubits are actually in situ tunable by the presence of these lines, you can compare a qubit that is actually embedded in a network of couplers and subjected to its own control lines carrying noise, to a qubit that is fundamentally isolated and not affected by flux noise. Let's see, this morning I was just thinking out loud about a huge number of experiments that I guess you guys now are gonna endure in order to tune up such a processor. For instance, yeah, you will basically perhaps implement randomized benchmarking or cross entropy benchmark, or you may want to try to run supremacy style experiments or boson sampling, which are also a good way to start getting the hands dirty. Or you want to experiment with quantum error correction or some of its substeps. This QPU is actually already optimized for performing error correction. The couplings and the topology is already optimized to perform the typical surface codes. But also, even in order to arrive to such a complex experiment, there are a lot of sub-steps that are important. For instance, you need to learn how to do parity check using 2 qubits to monitor the state of a third one and be able to detect an error. Or you want to optimize the efficiency of the readout shape by exploiting the presence of one of the parametric amplifier at the output of each of these feed lines. You may want to start playing with 2 qubit gates, for instance, venturing out of the comfort zone and trying to realize the so-called Toffoli gates, which is quite a beast and require quite some additional sub-steps. Or even more in the frontier, going beyond just 2 qubit gates, one may want to venture in the realm of multi-qubit gates, which is something that seldom is addressed due to the complexity. But I think fascinated by the opportunity here that this is truly a research lab, an open lab, and there may be students or PhD or postdocs that are coming with their own idea and basically use these as a quantum platform where yeah, there are opportunities at every step, even just in the act of tuning up the processor. There are many smart routines to monitor the status of the QPU. For instance, yesterday visiting the lab, I noticed that next door is the laboratory of INFN, and they had beautiful charged particle detectors running, monitoring on screen the direction of cosmic rays. But one may ask, what does it do with this processor? It's such a different energy scale, different domain, but actually it's becoming more and more evident that because these devices are quantum, they're sensitive, they operate at the smallest energy scales. Well, guess what? Cosmic rays are actually so incredibly energetic that they're able to produce errors. And so one may think that even just in the act of developing single qubit rotation optimization or T1 experiment, one clever student can actually start using the QPU as a event detector, making groundbreaking research in this field. Because having access to the fridge and the hardware Then the next question is, can we actually alter the shielding? Can we collaborate with experts in gamma ray to see concomitant event or to put together a number of experiments around the technology, around the quantum machine to progress the technology as a whole? Well, the list of things I was thinking continues quite long. I mean, this morning we learned how much important is the entanglement. And well, guess what? Any sort of quantum process is in principle simulatable in a quantum processor. So if you want to start easy and you want to verify Bell inequality, that's very possible. If you want to create GHD status among the qubits, I guess. If you want to practice with teletransporting information between one qubit and the other, you're able to schedule your gates and do the experiment. Another important topic is how large an entangled state can we make? How many qubits we can put together in a single entangled state? Well, coherence times of these chips have an average of 40 microseconds, and a gate time typically just above 25 nanoseconds. This gives you quite some time to propagate entangled states over a large cluster. But again, because you are doing it by yourself, interesting questions happens. How do we start? We start from a corner, we try to propagate, we start creating entangle at the center. Perhaps we exploit the fact that there are 4 cores and we can start creating entanglement in a parallel fashion. And this has quite some implication. It's not just fundamental questions, how large is the entanglement state, but for instance, in advanced error correction states, there are even concepts with funky names such as entanglement factory or entanglement times. Basically, in an error correction, you always suppose you have an infinite grid, but the reality is that there are edges of this infinite grid. And so at the edges of error correction scheme, there should be sort of injectors of entanglement to keep the density of this resource to a high enough level to be actually performing interesting computations and not just something that is classically simulated. And yeah, all this before even starting to discuss the frontier of doing simulation of small molecules or other applications, other techniques that are poised to be the real game changer as soon as we have enough qubits. So having dwelled a little bit on what the group here is going to experience in a few years, let me go back to our foundry services, which is basically maintain a very high quality control on the fabrication techniques so that we can accommodate customers that are coming with their own Hamiltonian, their own quantum mechanical problem, and they want to have a fabricated device. Perhaps asking the inclusion in the processor of particular topology or filters to better have high fidelity readout, such as the Purcell filters, or add elements in between the coupling elements, such as tunable couplers, that are then enabling better 2-qubit gate fidelities. And we can do that because we have quite a good control over over the established microfabrication processes. So, for instance, a customer can directly ask for particular EJ, Josephson energy of the Josephson junctions, and we deal with the realization of the suited lithography or design and lithography for having high quality Josephson junction. And also, well, having the advantage that the processes are continuously maintained and also developed on high quality or the highest quality superconductors material. So our vision is that by the end of this decade, well, we want to have a solution that has not only a lot of qubits in a single fridge, but also have the option of being multimodality and multi-node. So in this representation, the fridge has optical fibers that link different computing nodes and perhaps different modalities in order to have the best of each world, because clearly superconducting qubits are leading in terms of the computing processes, but it's also quite clear that that it may be needing some assistance when application requires, for instance, large quantum memories. And those are modalities that are supported by, for instance, trapped ions or trapped neutral atoms. So one of the way in which we need to step away of classical approach in order to reach the utility scale is the lateral interconnection. As the qubit count increases, if we keep addressing the input-output from the periphery, we reach quite soon a situation where, in order to reach with signals the interior of the QPU, well, the signal lines are crowding and they are passing in close proximity to other elements, and this produces quite some crosstalks, unwanted signal go to qubits that shouldn't be addressed. Moreover, if this interconnection comes from the periphery, well, then the periphery is not available to connect to more and more qubits. And so our radical solution is actually to go completely 3D, where each qubit has its own governing drive lines and flux line, and they are going directly vertically, never fanning out. And this creates quite some space in the vertical direction, still realized with silicon and superconducting materials, where we can actually add features like the filters, the conditioning, and the amplification that we discussed with the tuba in a completely new way, which allows for scalable solution, creation of a module that then enables for more tiles of qubits together with their vertical routing to be added on the periphery. So a little bit on this quantum open approach, which is also beautifully embodied in the laboratory here in Napoli. I believe we are at the infancy of quantum technology, but there are quite some parallels that we may want to draw from where we were in the early semiconducting era. And so in the 70s, for instance, there was the beginning of the IDM, so players that were specialized in components, where before there was a vertical integration era. There were the monolithic servers or the monolithic early days implementation of computers. And this IDM era is really what drove the innovation and the economy of scale, but also it drove the specialization and the way to overcome the incredible complexity of the devices that are nowadays then giving us societal changes through classical computing in this case. And what we believe is that also for quantum, this is happening. There are a lot of players at every level of the stack. So if one wants to build your own assembled quantum computer, it's nowadays possible. You don't need to reinvent the wheel. You don't need to, well, of course, if you have a brilliant idea, you should pursue it. But you don't need to try to reinvent every single step. You can focus on the layer of the stack where you can play your best. And so you can customize your build, you can upgrade it, you can be sure that you will find individual best components. And at the same time, this becomes affordable because of the specialization. And so in this idea, in this frame, we put together already quite a number of systems. For instance, one with the system integrator Kilimanjaro in Spain, where we placed a quantum computer attached to the high-performance Mare Nostrum supercomputer in Barcelona. We are, since a few days, also in Jülich, attached to another supercomputer from the Jülich Forschung Centrum for Supercomputing. We are also proudly active in the Open SuperQ Plus efforts of demonstrating 100-qubit quantum computer by the end of the next year, and other implementation. Yeah, one of them is actually the laboratory of Professor Tafuri. I think we understood the potential already a few years ago when for a very brief demoing of a device in kind, a very short turnaround of a week of measurement, Francesco and collaborators from the Quantum Academy, they basically put together an algorithm of quantum error mitigation that is now published, and it was, I mean, one of the first things that I noticed about this new lab is the experience and the thoughts that went behind the creation of this laboratory. First and foremost, it's highly secure and has a sophisticated system of intrusion detection and IP infrastructure connected to the backbone, already understanding the importance of cybersecurity and being connected to the nodes. Another strong point of excellence that maybe wasn't mentioned so much and maybe deserve another inauguration is the facilities and the community around. I mentioned the Quantum Academy that we also support as Quantware. The creation of a clean room at Via Claudia, which is another big part of the community that really excites me for obvious reasons. And the idea that students are able to come, propose, and operate machine at many different levels, from the algorithmic perspective to foundational quantum mechanics, or even to change the configuration of the filters to explore ways to optimize this quantum machine. This is a tremendous opportunity, I would say. And then definitely from one opportunity comes many more. One of them is a fantastic Pathfinder project that we have together with Unina and the University of Copenhagen as partner, and a few other startups supporting the efforts of implementing ferromagnetic and ferroinsulating materials into Josephson Junction with the main goal of offering an alternative scalable path to quantum computers based on superconducting. And this is, once again, an opportunity for pulling technology or science from the academia to real application, and for Napoli also represents an opportunity for developing this in a more commercial approach. So again, the importance of the ecosystem to build the hardware and the infrastructure and share results and make an important progress in the field. Thank you.
Thank you, Professor Nessuno, for the very interesting presentation. Next, Stefano Paletto, Director of Quantum Engineering Brigade Computing.
Yeah.
Working. So sorry, I don't want to be rude. I put a timer. So I know how difficult it is to be a shy man.
We can go beyond. Absolutely, yeah. Yeah, until half 12.
Yeah, then we shift it up. Yeah. Okay. Thanks. Thanks everyone. Thanks for the kind introduction. Thanks for inviting me. It's a real pleasure.
15 minutes. It's okay.
I try to. Yes, they determined 20 minutes. I try to shrink as much as I can. Yeah, I understand we have a little bit of time. So, yeah, thanks for inviting me. It's a real pleasure to be here, and it's great to see that Italy is moving in this direction. I've been waiting this for a long time. I've been working in the field of superconducting qubits for roughly 20 years, a little bit more than 20 years. It's been more than so I guess a little bit more than 20 years now. I studied in Padua, and I fell in love with superconducting qubits when I read a paper with quantum computing. Let's say when I read a scientific magazine, the Italian version. I say, okay, this is what I want to do. And I asked around, I discovered there was only one group, only two groups who were doing quantum computing, and was in Rome at the time. So that's I moved there to do my master thesis, and then I did my PhD. I moved to Germany when I worked with Professor Ustinov, the first group who measured superconducting qubits in Germany. After that, I went to IBM Quantum. It was the very beginning. I stayed there for 2 years and a half. I was probably the number 12 to join the team at the same time that Jake and Beta and Jane Chow and other teams joined the team, eventually Rigetti. Then I moved back to the Netherlands when I worked there, with Alessandro Bruno, to just give this nice talk. And finally, I joined Rigetti roughly 6 years ago. I started with individual contributor, I became a manager and director 2 years and a half ago. So what I want to give here is just a simple story, a story of how we evolved our processors. Is where I was being essentially involved. I'm an experimentalist physicist. So I want to tell you the story of this one, just to motivate you, to give you an idea how exciting is the field and sometimes how much frustrating it can be. So where we are, you hear probably yesterday from our CEO, we are located in in the Bay Area. Up here near San Francisco, we have two facilities. We have the Berkeley facility that is essentially, this is a picture of the facility. We have the quantum data centers where we do all the tests of the large devices. We go from 9 qubit devices in the small fridges up to the 8 qubit devices in the large fridges. The same that you have here. It's an XLT, so we have the 84Q device up there. And down in Fremont, there's roughly 40 minutes drive, traffic. So we have our facilities, dedicated facilities. So this is allow essentially to do everything in-house. We have the chip design, the fabrication of the measurement, and we have a quick turnaround in production. For us, this was the key essentially to move faster in production. So this is an overview, a screenshot of our processor, the number of qubits on the x-axis, the quality. So this is the median to fidelity. So you take all the edges, all the 2 qubit gates you have here, and you take a median is here. The key point is our first processor was down here, roughly 90%. To fidelity, it was called Agave. And now we are publicly available. This Anchor 2 processor is based on different technology that we introduce later. It's 84 Q devices and it's reached the 98% Q fidelity. We are here with R&D devices. We reached this level above 99% times ago. But you know that you did something good in research when the whole team, the whole company is now building up devices in MQ scale. And every day, routinely, we cross the 99% psychological rates, but here we mentioned before. So in this talk, I want to tell you very briefly how we moved from algebra. We went up in scaling and we went up. So all the tricks that we use. So this was our first QPU. It's an 8 qubit processor, and the key elements you see here, it's a qubit. A qubit is just an artificial atom, 2 pads connected by just one junction in between. Nothing more than that one. We can change the frequency of the qubit by just sending a flux to a square loop up there. So it's a tunable artificial atom. We write out the atom with simple write-out method, LC. This is one of the first versions, because we are not using this anymore. We're using the planar architecture, but it's a resonance frequency, and depending on the resonance frequency of the element, we were able to detect if the qubit was in 0 or was in 1. We drive the qubit through a dedicated drive line. In this specific case, it goes through the resonator. We don't use that anymore. Now we have a combined way. We combine the flux line and the drive line in single line, and we drive through the cap. So we have a sandwich. The qubits on one layer and the driving architecture on the other layer. And finally, in this specific architecture, there is a coupling qubit that you can see here. The zoom, well, it's not great, but it's just a capacity cap. It is made by design. When it's fabricated, there isn't going to change. It stays there. You just have to handle it without. So Aspen essentially is the next generation. Is we take the previous one, Agave, right? This 8. You rearrange a little bit these 8 qubits in an octagon layer, right? The edges is a qubit. The vertex is a qubit. The edge is the connection. And when you put more octagon together, we came out with this. We call the octagon square architecture because there are squares in between. And if you see now, every single dot, every single qubit here is connected to everything. You don't see in this specific place, but when you imagine that this architecture that is becoming larger and larger, now we have connectivity free all of them. And this is an overview on our processor, where we decide to go alternating the qubit, high frequency qubit, low frequency qubit. It was a fixed coupling architecture, so that we designed the qubit coupling, and then this work we have been using. There is a problem there, or a challenge, let's say. We don't talk about problems, but challenges, and how to turn challenges into opportunities. So the fixed coupling tells you that you want to have strong coupling, qubit-qubit coupling, because in this way we can do a fast 2 qubit gates and we reduce the errors. At the same time, when we do nothing between the qubits, we want to have almost 0 coupling, or very weak. Or on the other side, we want to detune the qubits. They don't have to talk. So that was the challenge of this architecture. And that is essentially why we have a high frequency qubit and low frequency qubit, because we want to keep this situation 90% of the time. When we do a 2 qubit gates, we need to go in this way, but we cannot change the coupling, so we're just moving the frequency using some tricks. So for us, the trick was to move on tunable architecture, and is essentially where I worked with my team in the last 2 years and a half to introduce this this different approach between qubits and qubits. Now there are the two qubits that we get here, QB1 and QB2. This is taken from this paper. It was the original paper from Will Oliver and group at MIT. And there is a pixel coupling, what they call G12. We cannot change this one, it's always there. But there is another coupling that goes with 3. This element, what is the tunable coupler, is indeed another qubit. It's placed between two qubits. And by designing the capacitances and frequency, it turned out that it mediates the interaction between QB1 and QB2. So we have what we can call a virtual, and the total coupling between the qubits is the sum. Something that is fixed and something that is true. So if we design properly all the elements, it turns out we can change the coupling between positive and negative. So there is a specific frequency of the tunable coupler. This special element here, if we pack that element, a specific frequency here, the two qubits are indeed not coupled at all. And when we want to implement the 2 qubit gate, we just move the frequency of the tunable coupler. Now here, where we have a 15 or even 20 megahertz of coupling, so extremely strong, and we can do the 2 qubit gate. So if we go back on the previous slides, we want both a strong coupling, high coupling, depends on what we're doing. This is exactly what in Unina, we change a little bit architecture. We introduce what is the floating tunable coupler. If you look at this one, the tunable coupler is grounded, right? But we use something that is floating, has 2 pads, both for the qubits and for the tunable coupler. It makes essentially 2 big changes that for us was very. If we design an architecture like this, symmetric configuration, we put the tunable coupling something that looks symmetric compared to the junction. We have that the G equals 0 condition, the qubit-qubit interaction doesn't happen, but it's 0. In this specific configuration, it happens when the frequency of the tunable coupler is lower than the frequency of the junction bits. In this other configuration, the G equals 0 condition happens when the frequency of the tunable coupler is above the frequency of the qubit. It seems, yeah, okay, it's just a frequency, we pack whatever we want. Indeed, it allows us to have bandwidth, right? We have without the resonator has their own bandwidth, the qubit their own bandwidth, and now the tunable coupler needs to have their own bandwidth. So we have the flexibility to play this one. But what was extremely important for us is, if we go back to this, this element, the G12, is the coupling QB1, QB2. This is fixed by design. The 2 qubits needs to be very close in the chip to allow that G12. In this situation, it's not necessarily needed. There is another way that coupling is generated. We don't go into details here, but it means that the 2 qubits, QB1, QB2, now they can be separated how much as we need. Even this seems trivial, why do I want to do that one? I want to pack everything together. It's because there are a lot of control electronics we have to put on the chip. So having the flexibility to move the qubits far away is important. How we see later, we can even put the 2 qubits in different chips, different wafers, and having coupling between them. This is going to work. So essentially, the floating tunable coupler is now at the core of our latest architecture. And this is what it's called. It's called ANCA family. It's the 4th generation at the gating. It has the main advantage that we went from the Aspen fixed coupling connectivity 3. We went on the ANCA tunable coupler elements and now connectivity 4. So this is ready for error correction code that Sandro presented before. And this is real photo picture of our device. I put here the colors representing the qubits and tunable coupler, just for you to see what it is. All of these are the qubits in between the other tunable coupler. So here the reality for qubits, as Bruno said yesterday, there are indeed way more qubits. If we count the tunable couplers qubit, there are 130 tunable couplers, the reality for qubits. So there are 84 computational qubits, but more than 200 qubits. So this was the key. If you go back to our plot, you see the right number of qubits and fidelity. Down here, this is the line, right? And when we have the static coupling, it was everything was fixed. We have to detune the qubits to keep them isolated, and we have to implement the gate. It was so. With the tunable coupler, we cross the line and went back to the above. So this is for us the key element for sampling, really standard way. So the other question is, how do we go larger? How do we increase the number? Right? Do we go monolithic? So if we start again with our architecture, we can imagine that we put 80 qubits together and we have a monolithic device. Yeah, we have 80 qubits, 80 resonator, 160 German junctions, so 106 couplers if you compare them. So each component has a fails, right? Clearly, we cannot go as large as we want because just one component fails, we have to go away from the chip. So we decided to go on what we call a modular architecture. It has right? Qubits are on different chips, so we can really cherry picking after fabrication of devices like this, 40 qubits or 80 qubits, something we are really confident it's going to work. And we store them on a carrier chip. This carrier has just the function to interact, make an interaction between qubits that are from one side and the other. So for us, the advantage here, we massively design and fabrication small chip that we cherry picking for fabrication what is better, and we assemble both together in a way that we want. If we take a single unit that's 40 qubits place, we can put units of 40, so 40, 80, 120, and so on. Processor, but put it together. This is a real image. Again, we tried with 2, but in this specific case, it was possible to go up to. We have the first demonstration. You can ask, okay, I have qubits on one side and qubit on the other side of the buffer. If I really want to have a processor that looks like a unique, right? It's only one monolithic model. I need to have the same fidelity of gates between 2 qubits and separate gates. The way we did that was just a superconducting layer of the guide chip here is cross section. The qubits are these little dots and here to different vapors. And these green layers, the superconducting layers, a capacitive coupling, parallel plate capacitors, but there is vacuum in between. And it's mediated interaction. Now, we measured 2 qubit gates in this specific gate, and we found that performances are the same fidelity of what we have on it. So that's why, if you look at this plot, right, we managed to stay with the same fidelity on the blue on the Aspen, but then here we went on Aspen M, where M is modular, that is M level. See, so the fidelity remains the same, but the number of qubits counted went up. So this was the visionary. We wanted to scale in this place. Okay. Question now, go. Okay, we introduced this tunable coupler. What do we do with this? This is fixable. We're going to do everything away. We need to invent something else. So for us, it was the next question after working on tunable coupler is how do we create a tunable elements between different chips? And this is what we did essentially. It's the tunable coupler between chips. So we take 2 chips, right? This green and red, where we have the qubits, and we have the carrier chips. Now we break the tunable coupler, the yellow part, in 3 different layers. So half of the tunable coupler is on 1 qubit chip. The signal goes through a carrier chip and goes back to the other chip. We use the Indian bumps to connect the elements up here on the back. So the first question is, can we have again G0 condition? Is there a specific configuration of the tunable coupler, including market frequency, where we can have the 2 qubit there and fit indeed the couple? And this is the plot. We have the coupling strength, the qubit versus the frequency, or here the flux bias, we can square loop, and see there is a G0 condition up there, or G. So this was for us pretty exciting, not only because it gives the possibility to recover our vision initially, but because the idea of the floating tunable coupler, that was the evolution of the tunable coupler introduced by MIT, it's working. Right? It's based on the fact that we can take these 2 qubits and put them far apart. We don't need the direct capacitors between them. And so what was the best proof than just put them into different chips? That's the thing. So this is specific configuration. If you look at how the tunable coupler is placed, is what is asymmetric. So there is one pad mainly connected to the 2 qubits, the other is there. So we decided to get a little bit more crazy and say, okay, let's see how much we can push. We went for the other architecture, that is the symmetric architecture, and now we are doing 4 transitions. So we have the tunable coupler that is on one chip, then it goes Indian bump to a carrier chip, back to a routing chip, again to the carrier chip and to the 7 qubits. And here there is an image. So there are the 2 chips here with the qubits, and the signal goes on top, it goes on other carrier here, routing chips, and back here. And even in this specific case, we have the G0 condition. So depending if we want to create the symmetric architecture, we have the ability of doing it. Due case fidelity, it goes the same values, about 99%. Of what we got in the link. So even in this specific architecture, where the 2 qubits are really 2 separate chips, the tunable coupler is connected up to 4 elements up here, we got more than 99% 2 qubit fidelity between them. So now if we go back to what I have here, is in my last slide, it's the overview. You probably understand this better. We started here with Algebra 8 qubit processor, connectivity 2. We went on all the monolithic architecture, that is the octagon-based architecture, connectivity 3, fixed pattern, from there, we went to the model architecture that allows us to scale out. How we managed to go up in fidelity, it was just going from starting cabinet to network architecture. It gives a lot more difficulties because there are more fluxes, more qubits, but we stay based on. We have an R&D device now, 93 devices. This is 99.3 to Q fidelity, and I want to say this is the medium. So if you count the 90 device, it has a total of 12 edges. So this is the median of 12 to this gate of this specific device. We went as high as 99.7 in specific case. But what we expect is exactly here. This is what is our goal of the company by the end of the year. We hope to release what is called Anchor 3 devices that needs to have a median to Q fidelity on 84 qubit processor, above 19%, the psychological threshold. And after that, we envision to go up with a number of qubits using the two architecture. And you have probably guessed from our CEO, Pastor Budo, that our vision is for next year to have the 300 plus qubits that will be based on this architecture and to work out. So this is all from my side. If you want to contact me, that's my email address, stuff.rigetti.com, very easy. If you want to related, just send me an email. And I'm happy to take any question even after I'm here all day. Thanks.
You open the question at the end of the session.
Definitely work for me.
Next speaker, Marco D'Alzeo, Development Manager at CPC.
Non so definire che riesci a faccio solamente.
Quando te induce?
15 minutes, 15 minutes I can make it.
Can you hear me well? Hello everyone, morning. Yeah, I want to be mindful of time, but I want to spend anyway a minute to thank and congratulate Francesco, Giampiero, Davide, Aima, Domenico, and all the guys and girls in the team. I mean, I had the privilege to spend some time with them, and I can tell you that they put a lot of effort and determination, top of expertise and competences. So I think that was the key to achieve such a great result. And I want to quote an Italian poet: "If you have such a strong determination and spirit, nobody will stop you. So please keep going this way." And this is my wish. I hope this is just a starting point, and the future is brighter and brighter. So I'm here representing SICK. It's the company I work for, the lab manager of the lab that we have here in collaboration with the Unina. SICK stands for Scalable Energy Efficient Quantum Computing. And I'm going to show briefly what we intend for that. But I think after all the talks, I don't have to repeat some of the key challenges that we all experience. Okay, sorry. So we need a lot of qubits. We need them to be performant, and we need to have low error rate, and that all comes into play with the scalability. In some cases, you need to go to thousands, hundreds of thousands, or even millions of qubits, right? So, this is you need to have a good strategy for that, right? And also, we worry about the energy consumption of what it will take, if you just scale in a brute force approach. So that's what all our mission is within our name, basically. It's important, the networking, and so as SICK as many other of the players in quantum, we have a global footprint. We have 3 sites. The headquarters is in New York State, in the US, but then we have another lab in the UK where most of the firmware and algorithms are developed, and the lab in Vietnam, which actually was the first that was started from SICK. And you have a lot of collaborators around different countries. This is extremely important. I have to repeat that. Okay. So our approach is to take inspiration from our fathers and try to repeat the evolution and the path that was taken to basically bring, basically a very faulty and super large digital computer based on vacuum tubes with only few bits in the middle of the 40s to billions of transistors, the processor that we have in all our pockets nowadays, right? And the key challenge was, okay, we see a lot of similarities. This is Google Sycamore computer, but you have seen the lab yesterday. You have a large fridge, a lot of cables, a lot of devices and components, the room temperature, electronics in order to run and to use such a system. And we believe this is not scalable to the number of qubits that we intend to reach. And so again, we want to take inspiration from that, and we want to. The major advantage was to go to transistor and then integrated circuits, and that's what also Stefan was showing before, right? You have this modular approach, right? And you use a multi-stack chips, where you have multi chips on top of each other. What differentiates us from others is that we want to move on that chip a large part of the electronics and the components that you see here in the figure. And the way we want to do that is to leverage superconducting cryogenic electronics that basically uses the same type of circuits that you use to build superconducting qubits. So same circuit elements. The Josephson junction is again the key element. But this, you can realize all the operation that I've done with the waveform generators, local oscillators directly on the chip. I believe that this is a great way to scale up. In terms of power consumption, this is not our slide, this is IBM slide, but this is one of their vision for the future, how they want to scale to 100,000 qubits. And you see again, there's a lot of fridges, a lot of racks of instruments. It's going to be a large room to use this, and also quite large power consumption. We are in the order of, I guess, 2,000 households, something like that. And with our approach, we estimate 20 households. But this is because the superconducting electronics stays most of the time in a non-dissipative regime. And so you only dissipate it in a very short time. You are more in the nanobots to operate a qubit. Right? This is a huge advantage. This is how our stack looks like. You have your qubits, and this can be any superconducting qubit. Actually, I'm going to show that we also want to integrate with other qubit modalities, not only superconducting qubit. And here you have, one of our chip carriers that contains the SFU single flux quantum electronics, digital electronics. As I will show, it's much faster in terms of clock rates. You can go to tens of gigahertz, actually hundreds of gigahertz in principle. Very low power consumption. It enables you to scale because you can need less lines. You can do digital multiplexing, routing if you want, and it's going to be very fast, especially with some solution. When you move everything on the chip, you can have access to the digital information within the chip. You don't need to transfer it back to room temperature to have access to it. This is one of the key aspects. We also have our own chip foundry, and we heard now this is important. I don't want to repeat that. We are the only chip, commercial chip foundry that makes SFQ circuits, superconducting flux quantum circuits. So around the world, there are other facilities, but these are either related to U.S. government or Japanese and China eventually. This is our roadmap basically, and we have deployed already a few systems. And this is again, these are just reference systems to validate and to show that the SFQ technology can be integrated with the qubit and can be used to scale efficiently the GPUs, basically. Well, first we had a reference system, which is just a conventional control. Then last year we developed and deployed what we call SIG Orange, which had a SFQ controller with the state-of-the-art single qubit gate fidelities and also the 2 qubit gate fidelities. although the decubic gate in that case were not done with SFQ control, but with conventional flux process. And we had a 1 to 4 digital multiplexer, meaning you need one correction line to run to drive for different qubits. And now we are developing what we call CPLO, which also includes the flux control for the qubit and also the readout. So this is something I'm going to spend a little bit more time because it's something we are developing here in Napoli, which also originated from ideas and hard work from Napolitan students. So I'm very happy about that. Well, you see that you scale up towards what we call green, which is what will have all the ingredients and components to do fault-tolerant quantum computing, or at least demonstration towards fault-tolerant quantum computers. So this SIGRAD was also our first, deployment of a system that we demonstrated with algorithms back more than a year ago. I just want to spend a little bit more time on what SFQ means. And here you see, this is not only us trying, to move the electronics at cold. There's a lot of effort in developing cryo-CMOS, but cryo-CMOS as CMOS dissipate a lot of power. So this is not really compatible to the temperature that required to create the right environment for superconducting qubits. So only superconducting-based electronics can be sitting at the same temperature stage as the qubit, and we have demonstrated that. Again, you see typical ID characteristic of Johnson junction. You have superconducting states of non-dissipation until you reach a maximum current called critical current, and then it switches to the normal state, and when it switches, it creates a pulse, voltage pulse, which is, the area of such pulse is a constant, a fundamental constant. It's called quantum flux. That's why I call it single flux quantum, and that's very fast pulses. I'm going to show something here. You see a little bit more details. It depends on the parameters of your junctions, but it can be as fast as 0.4 picosecond. If you translate to practical clock frequencies, or even exceed 10 times this is still 20-25 gigahertz clock operation. Whereas CMOS typically operate in the few gigahertz range, right? This is the thing. The energy estimation, you can also do the math yourself, but this you are in the joule, 10 to minus 19, 10 to minus 20 joule. That means nanowatts to actually operate at that qubit. And we have done experiment. We drive constantly qubit without any degradation of the gradient. So this is something we have already done. And just how it works. Typically, we create a pulse with a certain envelope shape, and this provides the energy to change the state of the qubit, or if you want to use the block sphere representation to generate a rotation around the sphere. When you do use our approach with SFQ control, what you do, you send a train of pulses, these very fast pulses, one after the other, and this is all digitally up to the point where the SFQ driver couples to the qubit capacitily and transfer the energy. But in this case, you are making small steps around the block sphere. So each pulses provide small steps. So you need a certain calibrated number of steps that are required to do a full rotation. And the advantage of being full digital is, again, towards scalability, because digital signal can be copied multiple times, and we have demonstration of secret SFQ base that go up to 16 or 64 bit. It means you can do a multiplexer that one line drives 64 qubits, and this is a huge. Just want to spend a few words on the readout, because this was the control before, but also readout can be done with SFQ-based system, maybe directly on chip. This is trying to solve a lot of engineering challenges when, so you want to, typically if you want to do error correction, but also integration with HPC, you want to have low latency of your signal, right? And if you have access to digital information already on the chip, you are cutting out some fraction, some hundreds of nanoseconds of signal latency. Again, this can reduce the overhead of some lines, and yeah, and another big advantage is that you can do it very fast. It leverages a few things. One is the detector itself, so this phase detector, which detects the phase of the signal that comes from a readout resonator that's coupled to a qubit. So you can infer information about the qubit from looking at the amplitude of the phase of the signal. In this case, we look primarily at the phase, and this is all controlled with SFQ. And also the signal that the readout of this detector is then digitized in the form of SFQ process. And so the goal here, and we have a project, a partnership with NVIDIA, is to create a chip-to-chip digital link. So from QPU and the SIG SFQ readout and control, you have already digital signal at cryogenic temperature, and you can create a link up to the GPU and the CPU of the Grace Hopper card. Basically, that's a very ambitious project, and this goes into the direction to HPC and quantum computing integration, which is one of the objectives of the National Center, as you heard. But also, it's also critical to perform a lot of operations of the QPU and ultimately the error corrections. The SFQ electronics, of course, as you can imagine, the big superconducting in nature, it's coupled very well to superconducting qubit modalities, and here are some of the players, of the major players. We are talking to most of them actually, and we are trying to integrate particularly our readout system with their QPUs. And SIG is actually starting a project with the National Center, so why not we can actually use the readout to couple to the 25 qubits QPU that now is sitting in the lab next to. And but this also couples to other type of qubit modalities. Another very kind of more straightforward integration with spin qubit, but there are other ways to couple to other modalities as well. Yeah, this is another project we do now, is to actually even improve the SFQ logic with a new type of logic, which is even more scalable to large scale. But I don't have time to go in details to that. But thank you for your time.
Avete passato? Resti che lo vedo.
Seguiti.
Okay, first of all, I would like to thank all of you for participating at the inauguration of our Superconducting Quantum Computing Center. And in this talk, I will try to give an overview of the experimental activities at our university, in our group in Napoli. These activities are carried out within several European research projects, which I try to mention in the next slides. But of course, most of the activities are carried out within the National Center for High Performance Computing. And some of these activities are carried out in collaborations with companies such as SIG and Quantware, and collaboration with the CNR, the Italian Research Council, in particular in collaboration with SPIN and ISASI institutes. So first of all, let me start from the production chain shown yesterday by Francesco, since this is our main goal. The know-how on the whole methodology, starting from fundamental concepts on the Gaussian effect as the key background for design, developing, fabrication of superconducting quantum circuits, measurements of superconducting qubits, and characterization of the coherence properties of superconducting qubits in order to perform quantum algorithms. And as a long-term tradition descending from the Antonio Barone School, our group is traditionally involved in several international collaborations and has promoted fundamental studies on macroscopic quantum behavior of both conventional and unconventional Gaussian junctions. In some cases, giving the first evidence of macroscopic quantum phenomena in special types of hybrid adjustment devices. And this has a strong impact, since the key elements of all superconducting qubits are the Josephson junctions, the nonlinear distributionless device, which under suitable conditions can be considered as a macroscopic artificial atom. And therefore, special types of hybrid Josephson junctions can bring new functionalities, also to the superconducting qubits. And our idea of a different type of transmon qubit is based on the use of tunnel ferromagnetic Josephson junctions. We call it the ferrotransmon. So basically, the tunability of the qubit frequency is essential for implementing qubit gates, and this is probably achieved by using DC squared and in the standard transmon geometry, and by applying a static magnetic field during all the qubit operations. So in the framework of a European Pathfinder project started last November, the Ferromon, our idea is to replace the standard tunnel aluminum junctions with tunnel ferromagnetic Josephson junctions in order to exploit the hysteretic property of ferromagnetic material. So basically, in the ferromagnetic junctions, by using magnetic field pulses, we can move along the magnetic field pattern of the critical current and measure different values of the critical current for the same value magnetic field before and after the application of the pulse. And therefore, the capability to tune the critical current and therefore the Josephson energy by using magnetic field pulse promotes the idea of a different type of transmon qubit where the qubit frequency can be tuned using pulses before the qubit operations as a reset operation, thus possibly reducing the flux noise and also giving the chance to remove the DC part of the circuit. Moreover, we have recently demonstrated that a special structure of tunnel ferromagnetic Josephson junction, the SISFS device, allows us to combine the typical transport properties of tunnel aluminum junctions with the hysteretic behavior typical of ferromagnetic junctions. And here the crucial result is that we can combine the properties of tunnel junctions in a ferromagnetic device without affecting the coherence properties of the superconducting electrodes and of the tunnel barrier. And therefore, this kind of structure can be easily integrated in the transmon geometry. Therefore, this idea is fully feasible, and therefore, ad hoc magnetic switchable devices are available for quantum circuits. Currently, in collaboration with Quantware, we are working on the final design of the ferrotransmon and on the design of the online chip of the chip line for the tuning of the qubit frequency, for the optimization of the qubit frequency by using magnetic field pulses. On the other hand, the flexibility of the Josephson effect allows to build ad hoc Hamiltonians, and therefore to allows to tune the potential energy of the whole superconducting circuit. And so, as mentioned before by Mark Warzeo's talk, we have recently developed together with SIG a new device, the Josephson digital phase detector, which is an example of how the flexibility of Josephson devices can be used to provide new ideas for both control and readout devices. So basically, this device is composed by two RF screens which share inductive load in the middle. And this kind of configuration allows to increase the number of degrees of freedoms in terms of external flux. And very briefly, this is the expression of the potential energy. So phi 0 is the quantum flux, phi 1 and phi minus are the sum and difference of the two fluxes of the two RF splits. And here the phase fit is the dynamical variable. It corresponds to the phase drop across the central inductance and can be represented by particle, the phase particle moving in this potential. And so for a beta larger than 1, by using the external flux, we can modify the shape of the potential and pass from a single well to a double well potential. And this is the crucial point for a phase detection protocol. This kind of protocol is based on 4 steps. The first step, the external flux is 0 and the phase particle is confined to 1 well of the potential. Then if we apply a pi0/4 pulse, the potential becomes harmonic. The third step, the signal that we want to detect, the micro signal, for instance, the micro signal coming from superconducting qubit, will interact with the Johnson digital detector. The phase particle will start a harmonic motion driven by this external signal. And finally, if we apply pi0/4 pulse, the potential becomes a double well potential, and therefore the phase particle will fall in the left or right well, depending on the phase theta of the signal that we want to detect. And since the phase B, the phase particle here, is related to the current passed into the central inductance, we can digitalize the output, the information of the output, by measuring the sign of the current passing through this central inductance. And therefore, all this has been experimentally demonstrated and is fully compatible with the idea of a hybrid classical quantum architecture, where superconducting digital electronics is linked to the quantum device and can perform specific control and readout operations. Moreover, the flexibility of the Johnson effect allows to realize cryogenic amplifiers which work at the same temperature stage of the superconducting qubit. And a hot topic in scientific community is based on the study of traveling wave parametric amplifiers, the TUPA. These kind of devices can be considered as a chain or a Johnson junctions, where again the nonlinearity allows to increase, to amplify the signal of the microscope. Moreover, these kind of devices can be used also to study other fundamental effects, such as the harmonic generations and their effect on noise, and gain in tubas, which is the main goal of the European tuba project. Moreover, these devices work at 10 millikelvin, so at the same sample stage of the superconducting qubit, and therefore it is possible to achieve the standard limit for the noise temperature. And the first experiments recently performed clearly demonstrate the capability to enhance the signal to noise ratio and to improve the fidelity in the readout of superconducting qubits. So all these know-how, all these techniques are commonly used in our lab to study, to make measurements on single qubit chips and 2 qubit chips. And in some cases, these chips are realized in collaboration with the Chalmers University of Technology within the Quantera project Superlink. And here I would like to stress that these devices are realized in Chalmers, but based on our designs. So designs that are realized and electromagnetically tested by our PhD students. These are examples of typical 2 qubit gates used for standard characterization, for optimization, calibration for both control and readout. And finally, in the last month, we have performed measurements on a 5 qubit chip, the Soprano chip provided by Quantware, where the qubits are in the star geometry with low, intermediate, and high frequency. So basically, on this device, we have performed a hybrid classical quantum algorithm for without error mitigation. So we know that noise is an issue in these devices, especially when we increase the number of qubits. So basically, by taking advantage from the state-of-the-art classical computational techniques, it is possible to identify quantum errors and mitigate them a posteriori after running many times the quantum circuit, so the sequence of the quantum gates. And therefore, in collaboration with the quasi group of Professor Gianni Campora, we have provided a principle demonstration that classical techniques can be used for quantum error mitigation for single qubit gates and 2 qubit gates. So basically, in order to recognize the readout error factors, we have performed repeated initialization computational basis experiment. And fuzzy clustering algorithms, this kind of machine learning classical algorithms, are able to identify the best mitigation matrix correction, thus strongly improving the output of the quantum circuit. So, as mentioned also yesterday by Francisco, this is only the starting point. Actually, we have installed the 25 qubit chips provided by Quantum, and we are going to see our new machine, our new infrastructure in the lab quite soon after the end of the session. But our goals for the near future are to scale up to about 40 qubits by the end of the year. And moreover, our choice, the choice that we have made to have a modular approach, allow us to perform different experiments at the same time. Therefore, we have the chance at the same time to develop novel hardware and also to implement novel quantum algorithms. Of course, this kind of infrastructure is a public, open infrastructure, quantum computer, and therefore we are open to collaborations with companies and research institutes. And more long, the next goal we have is also to interface our superconducting quantum computer with classical computers and classical supercomputers. Finally, it is really important to mention that the nanocenter facility at the engineering campus of Claudio is almost ready, and therefore quite soon we will have top facility equipments for the realization of many different types of devices, including superconducting qubits. Therefore, this means that we can realize our device in-house. And therefore, there will be another inauguration quite soon. And let me thank all the members of our group. I would like to say that it is really exciting to work together on these issues, to address together this issue at the frontier of quantum physics and quantum computation. Thank you.
Thank you, Dan, for your presentation. The last by Massimiliano Dispensa, Chief Technology Officer of Quantum Technology and Electronics Lab at Leonardo.
Grazie. Ok, anzitutto grazie mille a tutti, agli organizzatori. Thank you very much for the invitation. Okay, I'm going brief very quickly. It's quite late, so the idea is to give you an overview of an experience you had with a specific platform in quantum computing we had in the past, and it's to us is also a model for a potential cooperation we may have with this group, with the Naples Superconducting group. So just a quick overview of the strategy we generally have when we decide to go with new research streams or new research activity in quantum technology. We have definitely a cooperation that match and a matchmaking between quantum solutions and needs from the division. Then this defines research streams, which is not just uprightly defined by the technology, but it should match some specific needs for future product in terms of roadmap, product roadmap. Then first action is define internal investments. The second one is definitely, because it is definitely another value which is apart from any financial consideration, is having national and international networking and being incorporated national international project. Already yesterday I gave an overview of how we are arranged. We are based in Rome as a quantum technology group. We are cooperating with the other and then there is another group in optronics in Florence, and we also use the HPC in Genova. And okay, so these are the four research units we're working on. Yesterday already talked about the quantum QTD device, proprietary device we developed in the first one, or entangled-based imaging in the second one, or atomic clocks in the cold-atom atomic clocks in the fourth one. So quantum computing is one in which definitely is the only one in which do not build up our own proprietary hardware, but we have a very strong cooperation, and our strategy is not definitely just to use time from cloud services that could come from, could be D-Wave Quantum Annealer or IBM or something like that else. But what I want to show you, it's, okay, this is just the project portfolio we have in all of this activity comprising computing. And okay, we have okay. First of all, we have a definition of the kind of hardware we need. As to the type of services and products we develop, we may have needs for two types of computing hardware. First one is the need is a type of hardware which needs compactness, integrability, room temperature operation. And this is referring to the first type of use, that is hardware, computing hardware operating on board platform, on board unmanned system, vehicles, hardware, satellite, fast data processing, edge computing. The other one is large cloud and HPC systems for big data, for training AI models, for decision support, command and control. Totally different characteristics. The second one, of course, could be even bulky in terms of size and weight, but no problem to integrate cryo cooling, as it is also something that is integrated in another version with a standard, with common classical HPC. But need to have a network integration, while the other one could be standalone. The number one type could be even standalone on the platform. Okay, and hybridization with classical APC. So I will show you that we had a first experience with the first one, with developing solution and designing device together with other partner of hardware, quantum computing hardware of the first type. As to our internal analysis, we considered that and concluded that this kind of integrability and room temperature potential could be found, first of all, in photonic quantum computing, Okay, again, this is what I'm going to show you. These are just use cases, very general. We found them in our product or services, logistics needs a combinatorial operation, machine learning for classification of data coming from our sensors, radar, electro-optics. Then physical simulation, as we also have in our lab, even in my unit, there are materials lab. We develop solution for aerostructural materials or which may be nanomaterials, composite materials. So the third one is a potential use. The fourth one, maybe longer term, is a cryptanalysis definitely. So, and of course, hybrid architecture in terms of use or the kind of architecture we want to integrate the classical computer. Okay, so I started to talk about the photonic platform in terms of the number one hardware, quantum computing hardware. I explained a few slides ago. So the main advantage is just potential interoperability on chip and room temperature operation. Of course, there are issues, quantum losses, but loss tolerance schemes have been proposed. One point is that we have to use definitely different way of programming, of implementing algorithms or coding the algorithms. It's not gate-based generally. The easiest and fastest way to operate is another one, as we have to take on with the fact that the gates come to be probabilistic. We have to use a different, the so-called one-way or measurement-based quantum computational model. That means not taking a set of qubits and acting on them with quantum gates, but having big clusters of state, largely entangled, and having them connected with nodes representing entanglement, and locally measure qubits, and then at every step having measurement, and then a kind of teleportation, and then having the subsequent measurement defined by the result of the previous measurement. So it's totally different way. So we started with a clear strategy of addressing this kind of platform, quantum computing, photonic quantum computing platform. We started from very basic establishment of the way we want to use the computational model. First, for instance, the fact that we don't want to translate from gate-based to measurement-based, but we wanted to implement a native measurement-based computation encoding. Then, of course, as you see very clear, first you develop the basis, then simulating on HPC the algorithms that we need and we see are interesting for us. Then even simulating the noise of the platform on the algorithm, so the noise of the photonic platform. Then having it implemented on real hardware. Then identifying a specific use case. And briefly, this is the general overview. These are the single steps. First of all, we identified a mass K-cut problem. Mass K-cut is a famous NPR problem that is very briefly is once you have a graph, is the problem asks on which are the ways in which you can separate the set of nodes in two sets or in the K-cut in K sets, and with the maximum cut of the number of edges connecting the nodes. Okay, this is very closely connected to data clustering application. So we started, and then can be encoded in a quantum Hamiltonian, can be addressed with QAOA, quantum approximate optimization algorithm, can be native, and so we made a first work in order to define and identify a way to have natively coding in MDPC. So the result of this was also a first paper that had a second step in, okay, as I said, let's simulate a specific algorithm, mass K-cut algorithm on our HPC. And this is what we have done, also having a benchmarking with respect to the VA-based, and there is also a cooperation with Polytechnic on Milan. We also funded a PhD for that. And then we already had very interesting information from that on what's the affordability in terms of timing, in terms of efficiency, respect to alternatives, and so on. Then, of course, bare simulation of the algorithm with totally forgetting about the noise of the quantum computing platform is totally useful, as you don't know what happens, or you cannot even forecast in a general way what could happen when you apply it to a real platform. So we had a combined work with Leonardo and Candela, who's manufacturing and building up photonic hardware, photonic quantum computing hardware, and University of Trieste. We modeled the effect of noise in photonic components, also considering measurement coming from Candela. We simulated the action of nodes on MFPC algorithm, working with Percival. We also made our own design of the optical pattern and layout. We experimentally, and then we are currently completing the experimental evaluation of the result on the Candela platform. Okay, the design, we also had the opportunity, even though we don't have our own platform, not to use it, the platform as just a cloud service user, but an actual designer who could give indication on the way the layout is done, on the number of dual rail gates, and so on. We also added lossy gates in order to better simulate and tuned the lossy gate, considering results coming from Candela's measurement, experimental measurement. And we defined which applications are feasible, robust, not robust, what we can expect. This is the result. There is a preprint of the paper made with the first paper. Then we are going to have the second one with the University of Trieste. We did the work with Candela. And then fourth step, and that's a part that we will see again in the fifth step. Then this is another point that's alternative. Trying to identify if there are alternatives to the standard way the photonic platform is used. It's an option to go for a non-universal, photonic quantum computing is well known, the boson sampling, but standard boson sampling has very limited applications. We identified a modified boson sampling approach. It's an adaptive boson sampling. This is done together with the University of Sapienza. It's the very first time that this kind of architecture is experimentally realized from our Sapienza beliefs, but in any other part of the world, where there were just theoretical propositions. And it's, to say it in a few words, we have different sections in which we have boson sampling, but we have a kind of mix of boson sampling and measure and one-way computation. In fact, we have at each section we have a kind of measurement, and the result of the measurement of the first section gives the setting for the second section of the boson sampling, or adaptive boson sampling architecture, and so on. So this has the goal to measure, to calculate the kernel of a support vector machine to be used for classification algorithm. Okay, and then we have the very interesting result, and it was the first time that we got definitely a solution of a classification problem, and it turns out to have I would say advantage, but a good comparative result even to respect to standard approach, and an interesting level of scalability. Okay, phase one is something that is a follow-up of all the work I've showed you in KCAT, Max KCAT, and 2AOA applied to, or MVPC 2AOA applied to the Max KCAT. We applied this in a way or another to a solution of a very important problem for us. It's rather multi-target tracking. And okay, there's a patent pending, so I'm not going to further detail. It's NP hard of the multi-target tracking is a problem that refers to the fact that when you use a radar, you have at each scan a set of points, then the second scan, second number of points that are at different position, and then you have to identify which are not, you are not interested in single points, static point, but you track. So you have to connect points of the first scan to points of the second scan in the most likely way in order to have this trajectory representing the actual trajectory of the physical object. So it is a really anti-hard when you go, once you definitely go more than a number of two scan. And okay, that's patent pending activity, and we are very satisfied because as we have seen, we moved for bare theory from even before, for a general selection of a kind of use case, a kind of application, a kind of hardware related to our products, towards the selection of a platform, of a hardware quantum computing platform, and then pass it through a long route of steps from theory to simulation to noise, and then to actual implementation. So, okay, this is in fact a general presentation of the route. We also, in the meanwhile, had even application to other optimization and data clustering algorithm on the same port. And okay, the idea I wanted to convey to the colleagues is that we are quite interested to have similar cooperation with the Naples group. So not just as an external and cold user of a service, but and as a partner that can give indication, can receive feedback, and then have a strong interaction. This is the kind of way. Okay, we are sure we can go. We have also other cooperation with Naples on quantum communication, QKD. So it's I think to me it's a start of a good journey to go to the.
We have 1 hour delay, but it doesn't matter. It's a very interesting talk, and we have a few minutes for discussion. I invite all the speakers to come here and for questions. Francisco, have you got a question? But just I go to the past. In all of these research activities, what is the contribution of engineering from the system point of view?
You mean?
Huge. Very large.
You can answer. And that's a very good point. Something that we see, that's our experience in Napoli, is that really something very important, very new, that engineering is also moving towards quantum physics. And that's standardized to go towards industry and in different domains. There are examples of already happening. And I think that's the sense of the question of Giovanni. And so the question is your prediction. How for sure we know that there is a lot of physics and fundamental science to be developed, and in every talk is very clear. And now the point is that how much probably offer we have some real applications. So all of you have given some kind of prediction now, the numbers for the community and for business. Alessandro?
Yeah, I mean, I think the path ahead is a lot of the hardware standpoint. I think it's a lot of engineering. I mentioned there is a big component of material science in order to continuously find the best material for the highest coherence, and also a lot of microwave and superconductivity in order to use the building blocks in around the non-standard domains, the 3D integration and avoiding cross coupling, being able to put together this good qubits in a larger architecture.
Yeah, thanks for the question. So, yeah, so indeed it's a great question because we face this, right? It's a difficulty as well. We rely a lot on physics, we rely a lot on engineering, and we have a transition, right? We're moving from academia to companies. So most of us, most of the physicists, have no idea how a company works, right? So we're trying to figure it out. We're trying to figure out to work with engineers, but we lack of the expertise, of experience. When does the physics end? When the engineering starts? We have to figure out this. And if we can work on that intersection, it's for society. So we rely very heavily on engineering, they rely very heavily on physics, and we understand how the boundary to what makes the real policies.
Yeah, I mean, in our case, in SIP case, we are taking a technology that was developed in the 80s as the SFQ electronics, classical electronics, trying to adapt to the quantum computing field. So it's really a huge engineering effort, but also there are some, we also rely on physics because you have to understand what are the limitations, how to mitigate with the limitations and so forth. But I would say that the effort on the engineering side is very, very, very strong, and in some cases predominant for the hardware as the other state. So this is the migration from academia to industry, and also migration from the physics towards engineering. But I think there is still room to learn a lot on the basic science point of view. And as a physicist, for me, building quantum computing is to understand better physics. I know there are a lot of applications, but for me, the best application is to know better the quantum physics. So this.
I would like only to mention that in our group there are people, PhD and researchers coming from engineering faculties, so from material science, electronics. So this is something that it is still emerging. I mean, and moreover, as you probably know, in our university for the first time in Italy, we have this master degree in quantum science engineering, which is somehow, I mean, the idea is to develop this new kind of profile, quantum engineering. So it's something in between physics and engineering. So it's
Yeah, it's it's at the core of what I anticipated at the beginning when I thought about our strategy that is always starts with the matchmaking between divisions and quantum solutions. So in fact, in the innovation labs, in the quantum labs, there are predominantly and mostly physics, but in the division, in the business division, there are a lot of engineers. The point is that is definitely a critical issue is how to have them interact and understand each other. The level, the background is definitely different. And this is a quite basic and fundamental issue that is an education issue. And that once now quantum physics is moving to application, we had nevertheless we have still the result of the education of past decades when the two were totally split. So quantum mechanics was only taught at physics department, while engineering has total different kind of education. The quantum engineering course that is started here in this university is very important. In fact, as our own experience, there is only one engineer in our group in the lab so far, but definitely I'm pressing to have to hire many more. And this person is coming from this university. He also had the thesis in our group, and then I pressed a lot to have it hired as soon as possible. It's coming from the Marcello Calaffi group. I was, in fact, talking just yesterday with him on how it was a big game for us, and the kind of interaction he can have respect to specific issue that comes from the life cycle of the system or other kind of issue, robustness, reliability, and so on, is something that is in his background, but it is looking at a glance, while in other cases, other person look at other things. So very important, very interesting, very good experience.
Thank you. Other questions? I thank you again. I would say we are a bit late, so let's say 2:20 here. Okay, 1 hour from now.
Il registro è già scritto. Abbiamo verso una molettina.
E poi condivido. Prendo questo.
Ah.
Sì. Ok, ci abbiamo a concludere questa seconda giornata e con essa anche questo sentite
tutta questa roba che non delle cose.
dobbiamo concludere questa seconda giornata e con essa anche questa festa, inaugurazione del centro e del nuovo computer. Io darei subito il via chiamerei subito il impatto nei prossimi relatori, ok? Prego, il nostro chair, Stato Baccio, presento io, poi magari mi presenta anche lui dell'Università di Napoli II, prego, pure lascio il posto, poi diamo in ordine il professor Paolo Cremonesi, Daniele, comunque sì, saranno delle slide sicuramente, Daniele Ottaviani, Shai Martinez, no, corretto, spero di aver pronunciato bene, Simone Deliberate e Giovanni Acampora. Io lascio la parola quindi al professor Fazio per la notizie.
Grazie. So we switch to English, right? So, okay, so okay, okay, like this. So, okay. So we start the last section of the meeting with the first presentation by Paolo Cremonesi from Milano. He's the leader of SPOC 10 of co-leader, yes, of the Central Nazionale. Please. Thank you. Yeah, please.
Perfect. Thanks. I hope you can hear me well. Thank you, everyone. And it has been a long, very intensive day, mostly about platforms. Now we're going to switch about the upper layer of the stack. So we will start talking about applications. And I would like to give you a brief overview of what we are doing, both from the point of view of Politecnico di Milano, but also from the point of view of the SPOC 10 on quantum computing inside the National Center on High Performance Computing. So briefly speaking, I will talk about three topics. The innovation projects that which are application projects coordinated by the SPOC 10 inside the National Center on High Performance Computing. I will briefly talk about the need for a quantum benchmarking platform and what we are doing along this direction together with the University of Padova. And as a last touch point, I will briefly talk about another initiative which is connected with the Osservatory of Politecnico di Milano, which are doing research from an industrial point of view in collaboration with the again with the National Center for High Performance Computing. As you may probably already know, inside the National Center for High Performance Computing and inside this SPOC and also inside SPOC 10, there is a specific budget to run a number of projects which are proposed and led by companies which are within the National Center. Here you see a list of the 10 projects which are currently running inside SPOC 10. And you see the different topics. Some of them are highlighted because these are the projects in which Politecnico di Milano is involved. And all of these projects are about the design of algorithms or applications. And these algorithms or applications are designed to be emulated or to be run on real hardware. It depends on the maturity level of the project and the application domain. What I would like to ask you is to look at the distribution of the companies which are involved in these projects, because this is something that we will see later on from another point of view. And together with these projects, inside Spoke 10, we are running another set of projects, again, together with private companies, which are funded by open course. Unfortunately, I had no time to put the list of all of them here because the open call was closed recently. But there are other companies running other type of application problems on Spoke 10. Switching. So this was the point of view from Spoke 10. Switching from another point of view, from one of the several research activities we are currently running at Politecnico di Milano, in the application domain. I would like to focus a little bit on a platform we are designing together with the University of Padua, a platform for the benchmarking of quantum computing applications or platforms. So here the idea is to design a platform that can be used to benchmark application and architectures. So if you want to compare two different versions of a quantum algorithm, or if you want to compare two different quantum architectures, or if you want to compare a quantum application versus a classical application. So this is the high-level goal, the high-level objective. And we have a number of lower-level goals in this project. And the first goal is to somehow push quantum computing applications closer to or outside, let's say, the traditional application domain that we see very often about chemistry applications or quantum mechanics applications and so on. So the classical simulation problems. Of course, we see a lot of examples of applications in the simulation domain. Why? Because this is the main reason why quantum computers have been invented, to simulate quantum mechanics phenomena. But we want also to somehow bridge a gap between quantum computer experts and computer science experts, because there is a knowledge gap which is quite broad. And we want to reduce the learning curve for non-quantum computing experts to be able to design and run quantum computing applications. And by having a common platform for the benchmarking of applications, we want to, let's say, stimulate competition among researchers in improving quantum computer research on quantum computing algorithms. Something that has been working very well for many years now on other domains, typically on big data and machine learning domain. There is a very famous platform which is called Kevo, which is a platform to compare different algorithms in these machine learning domains. And this platform has stimulated a lot of interest in research. So these are somehow some ambitious goals. And most important, we would like to set up a kind of common standard about how to run benchmarks for quantum computing systems. Think about what happened many years ago for classical high-performance computing, where the LIMPAC benchmark is the standard to compare the performance of different architectures. Or there are spec benchmarks for other type of architecture and so on. So it's a kind of call I'm doing to all of you here in this room to, let's say, try to work together to cooperate and to think about standards benchmarking approaches in order to compare either platforms or applications. I don't want to spend too much time on how we have designed this platform. It is a cloud-based platform where researchers can submit jobs, and these jobs can run on multiple different quantum computing architectures. And there is we're trying to design some user-friendly user interface in order to make it easy for researchers to submit jobs, to compare performances, and so on. And we already have 15, 20 researchers, mostly from the machine learning community, which are now using this platform to start approaching quantum computing and they are using this platform to compare their algorithms against each other, algorithms that run on quantum emulators or quantum platforms. Now they're simple algorithms because the platform is quite new, but the idea is to work on improving this platform. Last point, my today presentation, the third and last point is from the point of view of the Observatory on Quantum Computing and Communication from Politecnico di Milano. The main goal, I'm sorry, this part of the presentation I just copied and pasted some standard slides, so they are most of them are in Italian. So here the main goal is to understand if there is the opportunity to start some to improve some business activities within the Italian ecosystem by using quantum computing technology. And we are doing this type of work by doing a different type of research, not the research that we typically done, the people with a technological background do. So we do research by creating physical devices or writing applications and so on. This is the type of research from the management point of view, by interviewing companies, by analyzing business processes, business needs, and so on, and by building a network of expertise and experts in this domain, and by setting up a number of communication events in order to disseminate this. The team working in the observatory is coordinated by Donatella Sciuta, director of Politecnico di Milano. There is a huge team of people working on this, and the observatory is cooperating with a number of, let's say, entities. It's cooperating with companies that provide the technology. It's cooperating with companies that are interested in using quantum technology, and the observatory is also cooperating with research institutions, but also with the government, in order to provide information and to provide guidelines on, or to ask for information about future investments on quantum computing. So these are some of the companies that are cooperating within the observatory on the usage of quantum computing technology. Italian companies, or the Italian branch of international. So now I want to give you some numbers that are related to 2023 about the picture that the observatory has taken about this, what's happening from the applications point of view. I will start with a few data from the international point of view. And so these numbers are about the investment, how much money has been invested in 2023 in quantum computing technology. Of course, most of the investments, 75, was on platforms. It makes sense. And we still need to do a lot of research on platforms. So it makes sense to invest a lot of money there. And but still there are 25% of the investments worldwide which are on application or middleware stack. And it was interesting, but from this survey, what was coming out is the need to have a common framework in order to evaluate the different platforms. So this was something that has emerged by the interview with these international companies, which is connected with the benchmarking activity I was mentioning to you earlier. It's also interesting to look at which are the, let's say, industrial sectors in which worldwide companies are experimenting the writing the adoption of quantum computing for proof of concepts or for applications. you see that most of the projects are in the finance sector. There are second in line, we have application in the pharmaceutical and chemical industry. Makes sense. We have surprisingly, at least from my point of view, the automotive sector, and so on. You see the different industrial sectors that are investing in quantum computing, in the scouting of quantum computing applications. It is also interesting to see which type of applications these companies are, let's say, experimented with quantum computers. And most of them are using or are scouting quantum computing to solve optimization problem or to work on simulations. Makes sense, again. So typically, optimization problems are interesting for fintech companies, while simulation are typically interested for companies working in the pharmaceutical or in the material sectors. And then we have also a number of companies which are trying to investigate the usage of quantum computing for machine learning application domains for a number of use cases. And some examples are, some very common examples are fraud detections again, in the fintech sector. Now, this was the international picture. Now let's drill down and to look at what is happening in Italy. So this is the picture of the companies, not all the companies, but large-scale companies, Italian companies, that are investigating or working, doing proof of concepts on quantum computing. And here you see there is let's see the pointer. Yes, there are most of the energy is coming from consulting companies. They are willing to be ready to provide support to end user companies. Okay. Then we have companies from the production sector, from fintech again, energy and telco, logistic and retail company, and so on. So this is, let's say, it's trying to be. This should be an overview of the companies, the large scale companies that in Italy are exploring the use of quantum computing. But not all of them, let's say, are working in the adoption of quantum computing with the same level of intensity. Okay, so here you see that there are very, very few companies, 1% of the companies that we can consider them as, really advanced in the experimentation and adoption of quantum computing. Okay, in this top 1%, we have companies that have run more than one proof of concept. So they started with one proof of concept, they were happy with it, they move along with other proof of concept. These are companies where internally they do have competence. So they have the capability, the internal capability to manage this type of applications. There are companies that are currently running proof of concept applications. There are companies here, the curious companies that are starting proof of concept application. They have not yet started. So overall, we can say that, roughly speaking, 25 of large-scale companies in Italy are working with different degree of maturity on exploring the adoption of quantum computing technologies. But 75 of the remaining companies, they are not working or thinking to work on quantum. And what should be my last slide? It is curious to look at the correlation between the maturity of these large-scale companies in the adoption of quantum computing and their maturity in the adoption of advanced computer science technology. Not focusing on quantum computer, but from a general point of view. Okay, so you see that the companies that are using computer science in the most advanced possible way, so cloud computing, so on and so on. Okay, these companies are also the companies that are more mature in the adoption of quantum computing. So It makes sense, okay? So the companies which are mature in quantum computing are companies that invest a lot and are mature from a broader sense in the adoption of advanced computing technology. And this should be all. So thanks for your attention.
Thank you very much. So I have a curiosity. Yes, companies that are curious, but is something spontaneous, or do they contact experts in quantum info or quantum technologies? How is the process?
Typically, the curious companies are companies that attend events. Okay. Maybe maybe today here, just as an example, we may have a representative from a curious company. So companies that are not they have no knowledge about quantum computing. They want to learn, so they are curious to know what is quantum computing, which benefits it would provide. So this is our definition of curious company. So typically they attend events, or they ask for information. They ask for seminars and so on. Okay.
Thank you very much. So we can move to the next speaker with Daniele Ottaviani from Cineca.
Questa?
Thank you. So, good afternoon, everybody. Can you hear me well? Okay, I'm Daniele Ottaviani. I'm the head of the Quantum Computing Lab at Cineca. And today I want to talk to you about one thing that we really care, and that is the integration of the quantum computers into the existing HPC environments that we have right now. Because we see the quantum computers from the point of view of the HPC, and what we want to do in the next future is to integrate, to use a quantum computer as an accelerator for calculus. Okay, and that's the same way that we are using GPUs right now. We want to use in the next future quantum computers to perform better our calculation. So just 2 words about our quantum computing lab. So our mission is let's say it's the same mission of the Cineca. So what we want to do is to so the first thing is to give to our users resources on our HPC machines and quantum computing resources. Right now we can offer emulation on our supercomputer, on our Leonardo supercomputer, and access to D-Wave quantum annealers and Pascal quantum simulators online in cloud. Okay. Also, we want to teach our users how to use quantum computers, and then we organize, among other things, of course, courses in our Cineca Academy that is also reachable online. You can Google it, you will find a lot of courses, very, very interesting courses. And we participate to European and national projects with the target to develop libraries, software, and middleware, everything that can be useful for our users to install it on our supercomputer and to give you the possibility to use it for your researchers. Of course, in the next future, what we want to do is to give you also the access to real quantum computers like the one that Francesco has here, and we will integrate also his computer with a supercomputer. And precisely what we want to do is to give to our user the access to hybrid system, hybrid HPC QC systems, in order to use to exploit better all of these new things and to run hybrid HPC QC codes that are not existing right now. And we are working in the context of different national and European projects to write these new codes. Right now, if you want, we can offer you computational time on Leonardo, and you can use all these emulators that are already installed and accelerated by MPI, accelerated by the GPU, also with the library, with quantum libraries that are developed by NVIDIA and dedicated to GPU acceleration or acceleration of quantum applications. Then we are also you can also see here the Quantum Matcha T emulator, which Simone Montegero was talking about this morning. And we are also installing other things. And of course, if you want to install something, you can ask us. Or if you want, you can also install it by yourself. Okay, so we are going to install a quantum computer. In March 2022, we were elected by the JU to be one of the hosting entities for the action of the European Commission to give to some European nation the possibility to install a quantum computer in their data center, their major data center. Italy, if you see, Italy was one of them. The strategy of the JU was to, because right now we don't know precisely what is the future, the qubit of the future. So the perfect qubit that will be elected if will be a qubit that will be elected as the perfect qubit in the future. So what we want to do is to try the most number of different technologies that we have in Europe and integrate all of them with different quantum computers, with different supercomputers, and try them and give you the possibility to try all the technologies in order to tell us which is better for which algorithm, okay, for which code that you want to install. To try, for example, for the Italian action, we are targeting a neutral atom quantum computer. The France actually targeting a photonic quantum computer. The LumiQ consortium and Germany are targeted for a superconducting computer. Spain is targeted for a quantum annealer, and Poland is targeting for an ion trapped quantum computer. Okay, so with Leonardo, what we want to do, so we have our roadmap is this one. In the first half of 2023, we turned on Leonardo, that is right now the 6th most powerful supercomputer in the world. It has a capacity of 255 petaflops of power, peak performance, of course. And one thing that is very important, because now we are in the era of the heterogeneous computing, it is a modular supercomputer. What does it mean? It means that it's designed to be composed by different modules. Okay, so not only classical modules, so you can see that if you have to, for example, you want to use GPU, so you have to go to the module with booster that are GPU, etc. But also we will give to Leonardo a quantum module very soon. This quantum module will be composed by one or two super quantum computers. We have to publish some tenders to decide which quantum computer we want to install with Leonardo. But we are targeting, as you were saying, by the USPC action for a 100 qubit simulator or a 550 qubit digital quantum computer. This is what we are expecting from, and a superconducting quantum computer with 5 or 20 qubits. Depends on the market condition when we will publish the tender. In the future, we are expecting this new quantum computer at maximum at the mid of 2025. At the end of 2026, we foresee the possibility to upgrade our quantum computers. In particular, we want to upgrade, of course, if we will buy a quantum simulator, we will upgrade it with at least a mixed analog digital mode. Or if we will buy a quantum computer, we will upgrade the number and the fidelity and the quality, of course, of the qubits that are composing the computer. And also we will see in the future and after the 2026, if we want to upgrade also the superconducting computer, we will see. Okay. But what I want to tell you right now is the concept of integration between a quantum computer and an HPC supercomputer. Why the integration between these two things? Everything starts with this very famous paper that's by John Prescott that say that the quantum computers in our time, that is the NISQ, called the NISQ, noise intermediate scale quantum computers, so computers that are not very big and not very so a little bit noisy. So something in which you cannot, for example, run the Shor algorithm or the algorithm that are famous in the quantum literature. And John Preskin say that these kind of computers can be used as accelerators. We have no mathematical proof about that, but it's worth to try if we really can accelerate some application using the synergy between HPC and quantum. And this, of course, one example is a variational quantum algorithm that so you have your code, and a part of the code is the HPC is used for optimize parameters that are used to calculate to the exact gates that you have to use in the quantum computer in order to solve a problem. Another thing that you can do with the synergy between HPC and quantum is the mitigation of error, because as I was saying before, right now quantum computers are very noisy, and there exists some mitigation technique that you can use to increase the precision of the qubits and the precision of the results of your algorithm, and the HPC can be useful to correct in real time, let's say, the output of the quantum computer. So how can we integrate a quantum computer with a supercomputer? Okay, we have three ways, let's say. The first way is the standalone way, which the quantum computer is somewhere. You connect to the supercomputer with the internet. Of course, you have a lot of latency, but you can use the quantum computer and synergy with a specific computer also if they are not located in the same room. The other way is the co-located, so on-premise. So you have the quantum computer in the same building, let's say, of the supercomputer. You connect them with a cable, with another cable right now. And the third way is the tight integration, that is the on-chip. So you have the quantum computer inside the rack of inside the nodes of your supercomputer. Of course, this is the best way, but technologically speaking, we are not in the point at which we can do that. You saw the quantum computer that Francesco had in his laboratory is not small enough to be put into a node of a supercomputer. So what we are targeting right now is the on-premise way, okay? And what we have to do in order to integrate this computer in this way? Okay, so suppose that we have our supercomputer is composed by a certain number of nodes. Okay, these are nodes of a quantum computer. Maybe these are racks, but for sake of simplicity, let's consider them as nodes. And we have a quantum computer. So the first thing that we have to do is to physically connect them. Okay, and this is the easy part. In the process of integrating a quantum computer and an HPC computer, you can have you have always had the easy part and the hard part. The easy part is to connect them usually with an Ethernet cable. So you connect them and this is connected. This way, maybe, so in the future, we also think about to do some advanced integration, hardware integration of a quantum computer with a supercomputer, for example, bypassing the classical computer interface that is installed, that is built inside a quantum computer, because a quantum computer is not only composed by the quantum processor, but also with other classical things. One of them is a classical computer that contains the firmware and contains the operating system of the quantum computer, that is responsible to translate the digital impulses from the classical supercomputer into analog pulses for creating the gates. But if you think about it, we have a redundancy here, because this is a classical computer and this is a classical computer. So maybe one idea can be to bypass the classical computer inside the quantum computer and directly connect the quantum processor to the classical supercomputer. Of course, if you want to do that, you have to work in synergy with the manufacturer, because you will need a lot of help from them. And of course, this means also installing the firmware and operating system directly on the supercomputer. This is the most advanced way to integrate in hardware speaking, a quantum computer and supercomputer. Okay, so now Suppose that we connect the supercomputer with the quantum computer. Now what we want to do is to use the quantum computer. Okay. Also here we have the let's call it the softer part. We have an easy part and a hard part, let's say. So the easy part is to use the quantum computer directly from the node which is connected. So this right now will be our quantum node. You want to use the quantum computer, you access directly on the quantum node, and you use the quantum computer, you install an SDK or something that can talk with the quantum computer, you launch your Python code directly on the node that is connected, and you use the quantum computer with the node of your supercomputer. But of course, in this way, you're wasting the resources of the supercomputer. It's a thing that connected into the laptop, okay? So what we want to do is to use the quantum computer as a part of an HPC job. What does this mean? It means that you have to write a software, so an SDK that can also be also include the usage of some of the paradigm that allows you to use the other resources of the supercomputer, for example, API for using other nodes, or CUDAs for using the GPUs that are also installed in the node in which it is connected to this quantum computer. And of course, this is something that is a little bit more advanced, but it is what we want to do. So at the end, what we want to do is to give the possibility to use the QPU and it's the exact way that you're using a GPU. Okay, so, and the middleware, of course, another thing that we have to do is to include the quantum computer into the set of resources that you can use, that you can request when you are requesting resources to a supercomputer. You know that a supercomputer is not like a classical computer because it's used by a lot of users at the same time. You cannot launch your code directly in the same way that you're using your personal computer, but we have to ask for resources. If you are planning to use, for example, this is an example of a batch file. In this way, you are requesting a node, etc. What we want to do is this line here, a way to request to the system the node with the QPU. Okay, so this way, in the exact same way which you're requesting the other resources, you will allocate for your job, you will allocate the node with the QPU, and then you will run the executable that contains quantum code. More advanced, for example, if you want to use also other resources in this way, this is only an example, of course, it's only something that I wrote very quickly, but I don't know if they will be but something very similar. In this example, you're requesting 10 classical nodes, you're requesting the node with the QPU, and you're requesting 4 GPUs that in this case are 40 because you're requesting 4 GPU for each node that you're requesting. Okay, and this is what we want to do. So launching this executable with the 10 parallel processor and the QPU that is ready to be called when the code will reach the quantum part. Okay, so another problem is the efficient allocation, because one problem that we are foreseeing integrating a quantum computer with a supercomputer is the fact that the quantum computer is a rare resource. If you think about it, so we are also talking about GPUs, but in our supercomputer, Leonardo, we don't have one GPU. We have 4,000 GPUs. So if you log in our supercomputer and request for a GPU to use a GPU, you will probably find a free GPU to use. This is not the same with the quantum computer, because the quantum computer will be only one at the beginning, 2 at maximum, okay? So it will be a rare resource. If you want to use it, you will probably find some cube, okay? And this is normal at the beginning. So one thing to solve this problem, for example, if you have a QPU that is a little bit big, for example, a neutral atom QPU composed by 200 qubits, you can think of a way to merging jobs in order to start 2 or 3 different jobs on the same time. This way you can give to the users the possibility to launch their codes without waiting too much. It's an idea, of course, we have to think about it, but this is one of the problems that you are foreseeing. Another problem is the control of the shots, because the time of the shots are very different. For example, a superconducting qubits can do something like 1000 shots per second. The coherence time is very short, but a single shot is very, very fast. On the contrary, in the neutral atoms regime, let's say, you have a very long coherence time, but the time required for a shot is long. You can perform 1 shot per second, something like that. This is the order of magnitude with this. So in this way, you have different problems, because with the neutral atoms, for example, you have to find a way to free the classical resource in the meantime, because maybe you are using the neutral atom computer for 1000 shots, that means 1000 seconds, it's a lot, and you have to find a way to free the classical resources in the meantime in order to give them to other users. On the contrary, with the superconducting qubits, especially if you want to perform error mitigation, so control over the single shots, you have to modify the granularity of the Slorm scheduler, of the scheduler that you are using, in order to catch also these very, very fast shots and have the possibility to manipulate them with the HPC computer and then give back to the quantum computer the result. Okay, so every quantum computer has its peculiarity, let's say, that you have to respect when you are integrating it with the HPC environment. Okay, so now that I want to talk to you about something that I think that you know very well, because we talked about it a lot during this beautiful event. And I want to repeat that what we want to do, we are part of the National Center for HPC, Big Data and Quantum Computing, and one of the targets of this center is to connect all the data centers that we have in Italy in order to create a network of data centers that is reachable from each point of our state. But also we want to enrich these data centers with quantum computers. And right now we can say that thanks to the efforts of Professor Tafurio, of the other professors that are involved in building Italian quantum computers, Professor Mortangero with the Quantum Computing Simulation Center, and with our effort to integrate quantum computers with Leonardo, we will add also different quantum computers to this environment. And then we will also go to Europe with our let's say scattered data centers to connect all our resources to all the resources in Europe to have all the quantum computers and IT system for our environment. With that, I thank you for your attention, and thanks again.
Very fast question.
Yes.
In terms of location, I guess the problem is also about the environment. So if you put
yes.
If you put a quantum close to a lot of wirings, you may have more.
Yes, they're very fragile. You have to build something that can shield them from the humidity, from magnetic fields, etc. So yes, also the environment is very, very important. But the thing is that the manufacturers right now are becoming very good to build quantum computers that can be put in data centers, in HPC data centers, because of them knows this issue, of course.
Okay, thank you very much. And we move to the next speaker by.
Thanks a lot.
Thank you very much. From tools. We are a bit over time, so.
All right. Hi, my name is Shai Magnus. I'm from Cruise. And what we do is we build software to help physicists and engineers build quantum computers and MRI and other stuff, but that's not relevant here. So when we develop quantum technology, we start with design, then fabrication, tune up. We need to estimate the parameters, learn, calibrate everything. And then we get to generate an error buffer because our quantum computers aren't working as well as we would like today. And we want to understand why so we can make them better in the next iteration of hardware, right? So what can we do to make this whole process go a lot faster? Well, we built the Cruise toolset to do just that. So it has kind of three major blocks, and I'll walk you through them. One is a digital twin of the device and surrounding control electronics. The other is what we call Cruise OS, which is the whole breakup, the whole set of steps that you need to take in order to get from what is a physics experiment to a working computer. And then finally, Cruise ML, which is understanding from the data we get from the device itself, why isn't it working perfectly, right? So why is the handling error rate 2% and not 0.5% or whatever? Which means that then you can know what you need to do better in the next iteration. And now we'll kind of go through them. So let's look at the digital twin and what we can do with that to optimize pulses and do stuff like that. So we'll start with an example. So this is work we've done with Andrea Murphy from MPQ, and the platform is, of course, Rydberg atoms. And the problem is that the single qubit gates are actually really, really sensitive to fluctuations in laser power. So in Rydberg systems, doing global gates is easy, but doing kind of single rotations is hard. And if you take the fairly naive approach, then you can do gates at high fidelity only if you do fairly minor qubit rotations and the laser is extremely stable. Okay? And that's kind of the default way of doing quantum gates in the system. And the question was, can we make this more robust? So I can't tell you exactly what we did because this hasn't been published yet. But after we did what we did, which has to do with some sort of optimization for robustness, this is what the fidelity matters. So you get excellent fidelity virtually everywhere. If you have very high laser instability and you want to do almost a complete pi rotation, then it's not perfect. But the difference between this and this would be more. Okay? So this is what we can do with the digital twin. More specifically, it covers trap times and superconducting in the NV centers and silicon dots and also things having to do with MRI and other technologies. We can do all kinds, basically any effect you can think of that can affect the system, we're trying to put in the simulation. So things like 1/f noise and other arbitrary spectral noises and crosstalk and transfer functions on control lines and errors in the readout and crosstalks and just anything and everything that could affect the system goes into the digital twin. And part of this is having a realistic control stack. Okay? So let's say you have, I don't know, Zerk instruments, waveform generators. You can say, I have this type of box. It'll know the resolution in time, in voltage, what the response function looks like, what the noise spectra looks like. It already knows everything out of the box. And if you have something kind of custom, we can measure everything and then put it. So this is just some pictures to make it look pretty. So this is simulated 1/f noise. And this is having to do with the arbitrary control function. So you're trying to do a Gaussian pulse, but what you're actually doing, so you have these overshoots and undershoots and little wiggles, which actually are really, really important if you're trying to get 99.9 fidelity. Okay? So everything goes into the simulation. Now let's talk about the breakdown. One other thing, the simulation, of course, is fully differentiable, because when you want to run optimizations, it's very helpful if you can get the gradient of the fidelity with respect to, I don't know, the bandwidth of the performance. Okay, Cruise OS and the breakout. So what do we get here? So first, we have a library of a lot of experiments out of the box. Basically, everything that has a name and we are aware of, we input. And instead of having a list of names, you have a list of predictions. Okay, so everything having to do with single qubit, everything having to do with 2 qubits, 3-state discrimination in the middle for superconducting qubits. Basically, just about everything. Flux spectroscopy, cross-resonance bases, precompensation of flux, 2-qubit interleaved RB, you name it, we have it in the lab. Okay? But just having a long list of experiments is nice, but that's not the whole story. So you want to actually make it work. So we have this whole framework for connecting these individual experiments in essentially a directed acyclic graph, right? Kind of sort of a tree. This is actually a screenshot from the calibration of a superconducting chip that's running at Unit Research Center every day. You can see that most steps succeed, but sometimes a step breaks, and then subsequent steps don't trigger, etc. Okay. Now, of course, when you run this in your lab, you have your own experiments. So you can interleave or include in this graph your own experiments as well. So it's not just ours. Okay. And you can run everything, on a regular interval once a day, or you can say, just run this subtree now, or run this experiment now because I want to debug it because something doesn't work. So let's say in this example, this experiment failed. So you can go back and look at the specific experiment. We have kind of web dashboards to do this whole kind of stuff. You can look at the specific experiments, specific plots. And if you click here, it actually opens the specific Jupyter notebook that run the specific instance. So for every day that we run this experiment, we duplicate the Jupyter notebook. So when you look at it, it's the Jupyter notebook that ran this time, as opposed to the one that ran 3 days ago. You can see the data, you can debug it, you can rerun it, you can do whatever you need to get this thing to work. Really, really important, doesn't show. Okay, so I'll say 2 things that should have shown up here, but don't for some reason. 1, all of this runs fully locally in the lab. So you can run it off our cloud if you wish, but you can run all of it in the lab, meaning all the information about the device, anything and everything runs in the lab. We have no idea what you're doing. You can switch from trapped ion to superconducting qubits. We would never know unless you does. Second point is all the data that's accumulated here is saved in a database to which you have access without our software. It's just a database. It's using some available, off-the-shelf database, and you can access the data even if you don't have license. Okay. So you're not locked in. You always have your data, regardless of it. Okay. Of course, we also sometimes want to see how, I don't know, T1 or T2 changes a function of time, how qubit frequency drifts. Once we had a customer where they realized that their fridge was cycling temperatures because they looked up the plot of the temperature as a function of time over a month, and they saw kind of general oscillation. So this is very useful. Of course, you can render it yourself, but the database will give you the dashboard. You don't have to do it. And third component is CruiseML. This is the real kind of crux of it, which is, okay, I have a chip, it's kind of working, but it's not working as well as I want it to, and I don't fully understand why. And I want to try and figure it out. And then maybe I can do something about it. So what's the setup of the system that allows this? So initially, you have, of course, your device, and you can see here the control electronics. It's not just the quantum parts of it. And we create a digital twin. Now, the digital twin is based on physics equations, so the Schrödinger, Lindblad, whatever is relevant for the case. It's by the way, it's implemented in TensorFlow. It's a computational graph. It's not a neural net. but that means it runs on CPUs, on GPUs, scales to very large systems, as long as you have enough memory. In that respect, there's no magic. At the end of the day, the limiting factor is the size of the Hilbert space, right? Our simulation is aimed at maximum physical accuracy, which means that it's not going to compete with Simone's tensor networks, right? Because we're aiming at slightly different things. Right? We want to understand the physics, not simulate programs. So it's a different tool for different things. Now, based on this, you can do some optimal control, like we showed in the beginning. Then you take, because initially the model is not very accurate, right? We give the people in the lab essentially a big box of Lego blocks with which they set up their simulation. Now, initially you don't have the right values, maybe some of the blocks you forgot to put in, et cetera, et cetera. So you need to do some closed loop calibration. So of course we do that, and that's kind of the trio of experiments. Now, many times in many labs, people just stop here, right? So they maybe did some optimal control, maybe they kind of take pen and paper what the gate should be. They did some calibrations, the gates are working better, great, we stop. But we think it's not a very good place to stop because first, the fact that you even need to calibrate means that you essentially prove that your model is inaccurate. Because if the model was accurate with the hardware, you wouldn't need to calibrate. Second, the gates work better now, but you don't know why. And worst of all, you don't know why they're not working perfectly. Why do I only get 995 and not 998? Right? There is no insight. You kind of push the fidelities as much as you can, and then you go on to a guessing game of why can't they push it further? And the question is, how can we take this next step and understand what's the limiting factor? So what we do is we take all the data accumulated during calibration or any other experiment, put it in a database, and we do a step that's called model learning. Model learning is adjusting the model so that it best fits the data. Right? And conceptually, you can think of it like this. The system is, of course, stochastic, but our model is also stochastic if it has 1 over F noise and things like that. So what we can do is we can measure the statistical distance between the prediction of the model, which is a PDF, probability distribution, and what we got from the experiment, and we know there are error bars that have to do with shot noise or whatever, right? And it's the same way that, in LHC, they're always looking for 5 sigma deviation from the standard model. So we're looking at the deviation between our model and the system. And we can use this statistical distance as a loss function to optimize the model. And then you get a model that's a lot closer. And this is what I'm going to show right now. Oh, and after you have a reliable model, you can do something really nice with it, which is you can do an error bus. Meaning, let's say I have 5 different noise sources, okay? And I don't know which one is causing the most infidelity. What I can do with the reliable model is I can turn off each of the noise sources one by one and see by how much fidelity improves. And that gives me a quantifiable measure of how much does this phenomenon contribute to my infidelity, right? What if T1 went to infinity? How much better would my gauge? It's not so easy to judge given you have T1 and T2 and a host of other noises, right? And we give the tools to determine this. Now, of course, you can do it with any model, but if the model is not reliable in the first place, why do we trust the results? You first need to get a reliable model to then trust the results. And this is an example of model learning in practice. So we're trying to do a controlled C-gate, and later we'll talk about the sudden noise zero, which is kind of the cardinal bipolar pulse to do a gate. So we had somebody come to us and say, okay, I'm getting these for the CZ gate. This is my chevron plot, right? So this is, I think this is the 1-1 and 2-0 state, if I'm not mistaken. This is the duration of the pulse. This is the voltage. This is what they got. This is the way it's supposed to be. Why don't they look the same? it's not clear. So we set up a digital twin, and the digital twin allowed for, all the standard parameters that you have in the Hamiltonian, but it also allowed for things that you normally don't quite simulate. For example, the transfer function, right? Because there's a wire going from the waveform generator into the fridge. And that has an effect on the pulse, especially since this is a flux pulse, meaning it's a DC pulse, there's no carrier. And you're going down to kind of low frequencies, and that may be an issue. So what we did is we then did the model learning step. And you can see that now the digital twin has managed to reproduce what's going on. And it turns out that this transfer function is the prime component. Meaning there were some errors with the frequency and the coupling and stuff, but the transfer function is the prime component. But since we learned 83 parameters about the system from this data set, one can say, well, maybe you're just overfitting. Okay, so let's try to do another experiment. Instead of doing this square pulse, let's do the bipolar. One square pulse up, one square pulse down, a little bit of gap. This is the Vicario SLC. So this is how the new experiment, this is how the data looks. And this is how the simulation looks without relearning. Meaning it's using the model learned here to predict this experiment. As you can see, it's mentioned very well. But if it's a transfer function and I have a distortion, I can pre-compensate, right? And then I get this, right? So this is the ideal, this is the compensated distance. You can see it's very, very close to each other. Not perfect, there are some asymmetries here. So a very, very big step. So you do model learning, you learn something about the system that tells you what you need to do. I need to compensate for distortion. I compensate for the distortion, you have a much better. And then you can iterate again. So the cruise tool set has 3 components: a digital twin for optimal control, the whole bring up with a very big library of experiments, and machine learning and the model learning, which allows you to get a very accurate model, understand what's going on, get the narrow budget, etc. And this is how we accelerate the development. Now, if you have a lab and this sounds interesting, then talk to us. Usually, first step is set you up with a nice demo in the cloud, just so you can play around with the software on a pretend device to get the feel for it, and then we kind of install locally in your lab and what's happening. Thank you.
Sorry, the model learning means that you're also learning how the environment.
That's part that whatever is part of the simulation can be learned. So we can do, the gradient of the statistical distance between the model and the data set with respect to any of the model parameters, which means we can learn any of them.
Okay, thank you very much. Okay, Simone Deliberato from Quantum Italia.
We Napoli.
So, well, I start to thank the organizer for the invitation, especially to compliment the local team for really impressive results they have obtained. I think it's really an honor to be here in celebration of this very important result for the Italian quantum ecosystem. So, yesterday we heard both some of our colleague researchers and some representative of both Italian and European institutions mentioned the need for private funding in order to advance the quantum ecosystem. Private funding, which is important on the one hand to help select which are the most promising quantum technologies, and on the other hand to bring them closer to market. On the other hand, it has been highlighted how here we are talking of deep technologies, these technologies which put together both a high technological risk and a high product market fit. And as such, they require very specific kind of funding and a work of de-risking in order to allow standard private funding to fund those innovations. I'm here to represent Quantum Italia, which is a recent Italian company, the Italian funding vehicle, which has been created in order to try and fill those two gaps and try to improve the state of private funding for the Italian quantum ecosystem. I serve as first CTO of Quantum Italia. I also am affiliated with CNR and University of Southampton. So Quantum Italia is the first quantum studio in Europe. I define what I mean with this. Quantum Italia is the first Italian investment vehicle which is dedicated to quantum technologies. Our funding partners are Scientific VC, which is an Italian venture capital fund, and Quantumation. Given the audience, maybe not everyone is familiar with what a VC fund is. A VC fund is an entity which collects funding from limited partners that can be high net worth individuals or institutions. In Italy, CTP, in France, BPI, and then they invest money following an investment thesis. Normally, the more the domain of investment is technologically advanced, technologically deep, the more it is important that the fund is focused in order to be able, on the one hand, to have the knowledge and the skill to evaluate, to do a proper due diligence of all investment opportunities, and on the other hand, to provide not only money, so-called dumb money, but also to provide to the companies in which they invest an ecosystem and a lot of other helps which allow them to develop. Quantumation is the leading quantum investor, the leading fund which invests in quantum technologies. They created two funds. The first one, which was closed in 2022, which was a $91 million funds, and invested in 25 companies. Here we see on the vertical axis, essentially all major quantum technology startups, and here the different investors which invest heavily in quantum technologies, and this is Quantumation. We can see Quantumation invested roughly on the 30% of quantum startups worldwide, and I think they reach around 50% in Europe. Now Quantumation opened their second fund, which is they target 200 millions. For the moment, they raised 70 millions. The important difference between the first and the second fund is for this talk is this last line. Quantumation 2 aims not only to invest in companies, but also to invest to sponsor 3 venture studios. Because during their development and investment phase of the first fund, Quantumation 1, they realized that there are a lot of needs, a lot of problems to actually bring early stage quantum startups on the market. There is a problem that those technologies often they are so far from application that it becomes difficult to actually build a business case around them. There is the problem that the startups often have very high capex requirements. They need maybe a division fridge, which is very difficult to buy, to acquire funding to buy, while the whole concept is still very speculative. And so they decided to try and solve this problem by creating venture studios, so startup studios, entities which are able to provide to those startups or to those teams, they don't even, maybe they are not yet at the stage of a startup, all the support, both economic and in terms of other kind of supports, to mature their ideas up to the point in which they are ready for a venture investment. This is the first quantum studio that Quantumation helped developing. This started a couple of years ago. It is Superconducting in Sherbrooke. Now they are finally active and they started, they already got in the first batch of startups. It's a fairly large project, 40 million Canadian dollars investment, of which 29 millions of public investments. They have impressive facilities. We visited all the team, we visited them a couple of weeks ago. They have both classical and quantum computing capabilities, fabrication capabilities, and business training capabilities. So this is the first quantum studio worldwide, and we are the second. We are the first quantum studio in Europe. Now there are also others which are being developed. So we have two main missions as Quantum Italia. The first mission is the Quantum Italia Studio program, which is essentially what I just described to you. That is, we are a venture studio with the objective to take very early stage innovations, very early stage teams, and within 2 years, create out of them startups which are ready for venture capital investment. Then we have a secondary mission, which is Quantum Italia Incoming program, and that is to support the quantum startups which are already established abroad to establish activities in Italy, to enter the Italian ecosystem and enrich the Italian ecosystem. In order to accomplish those two missions, we provide direct cash investment. We can support them by our team of 20 plus professionals in legal, communication, grants, HR, essentially all the requirements that an early stage startup can have. We offer office and lab space in Rome. We have an internal program of business training for the teams. We offer an integration with this worldwide quantum studio ecosystem. For the moment, as I said, the Canadian one, but there are others. One in France has already been created by now, and there are others which will be created in the near future. And also the access to both quantumation and scientific ecosystems. I give examples of how those can be useful. So our facilities, for the moment, we have spaces in Rome, 1,000 square meters in Tecnopolo Tiburtino, provided by Innova, but we support startups all across the country, all across Italy. So this is the quantumation portfolio. Neatly divided in the different bands of the different quantum technologies and also deep physics, which is the band in which quantumation places all the startups which are somehow related to a quantum ecosystem, but they don't easily fit in one of the others. Given that this session is about software, I highlighted the quantum computing software startups. The ones listed in yellow are the ones which are already exited, so they have already been acquired. We noticed that one of them, Q&Co, has been acquired by Pascal, which is an hardware company of the same quantumation portfolio. So we can see how important it can be for startups to be in this ecosystem, in this portfolio, not only to be acquired, but also if you are developing quantum software, having direct access to multiple hardware providers. Pascal, Candela, Norcantic can provide not only useful information, access to hardware to develop and test software, and later on, eventually, also a quite natural way for exit. I'll cite more in details two of those companies, Qubit Pharmaceuticals and Multiverse Computing, with which we are talking for these Quantum Italia incoming programs, trying to bring them to Italy and expand their operations in Italy. So let's start with Qubit Pharmaceutical, which is a company which develops quantum software for pharmaceutical and drug development and drug discovery. As it's a very successful company, as quantum startup software go, and as many of them, their activities are divided into main branches. One only purely quantum activity, that is quantum software which runs on quantum computers or simulators of quantum computers, which is still at the R&D stage, and a quantum-inspired part, which instead is already in production stage and is actually used in various drug discovery programs. Qubit Pharmaceuticals has already a quite broad portfolio of potential drugs they are investigating, often in collaboration with other institutions, mainly in the oncology and inflammation areas. The team is now 50 plus people between Paris and Boston, and we hope soon Italy. They raised 25 million, collaborating with a number again of entities, both in the French and European context. If you want to hear more about Qubit Pharmaceuticals and more generally the application of quantum technologies for your pharmaceutical research, we organized the first Quantum Italia event in Rome for the 27th of June. In this event, there will be a representative of Qubit Pharmaceuticals, but also other quantum startups, Algorithmics and Pascal, and we will put them in contact. In the room, there will be mainly representatives of both academia institutions and a number of Italian big pharma that we hope will start collaborating. We hope to create collaborations between those entities, those Italian companies, and Qubits and the other startups, in order to foster and to facilitate their installation in Italy, the fact that they will create business in Italy. If you are interested to join, please write me or to event@Quantum Italia DC to get an invitation. Then I also mentioned Multiverse Computing, which is another software company of the Quantum portfolio. It is a company founded in 2019. It has grown quite rapidly. Now there are more than 150 employees with some turnover obtained in collaboration with a number of major corporate players. They have got in total more than 35 million euros of funding. We know that they are already present with an office in Italy, but we hope for them to develop even more their activities in Italy. Their main product, they actually develop tensor network codes, which they use in their two main products, Singularity and Compactify, to reduce, to allow to perform quantum simulation and to reduce the cost and improve the efficiency of those simulations. Okay, this is my last slide. Just to say, we are right now in Quantum Italia. It's only 2 months old. At least it started operations only 2 months ago. We are actually in the phase of accepting and evaluating the first proposals for both the Quantum Italia Studio program and the Quantum Italia Incoming program. So if you are or know interested teams that could wish to access these funding and support opportunities, or if you are from a foreign startup, a quantum startup, which would like to be helped to discuss about opening business in Italy, please write me and come talking with me. And we are also establishing partnership with both private and public institutions in Italy, again, to help create an ecosystem in which Italian research, Italian startup can thrive and can develop. And with this, that's all, and I thank you for your attention.
Just a curiosity, I heard that Nova Nordisk is putting a lot of money in quantum. Are you aware of this? No. So we move to the last speaker of the session, Giovanni Acampora from
Okay, Okay, thank you, Francesco Giampiero, for having invited me to this important event. And we are arrived at the last presentation of this event, but we have also arrived at the top of the quantum step, because now I will introduce you with some application that merge together quantum computing and artificial intelligence developed here at the Department of Physics at Ettore Pancini, where I am currently a full professor in computer science. I founded the Laboratory of Quantum Computing and Smart System in 2017, and I'm the founder and editor-in-chief of Springer Quantum Machine Intelligence. That is the first journal in the area of quantum artificial intelligence. And I would like to explain to you how artificial intelligence and quantum computing can be used together in order to solve problems. In order to explain this, I have to make a kind of introduction to artificial intelligence in terms of the different components of AI, the reasoning, the machine learning, and problem solving. Why? Because artificial intelligence is a computer science set of methodologies able to replicate by means of software some human capabilities: reasoning, problem solving, and learning. Okay? But what is learning? Learning is a human capability that use past knowledge in order to infer new conclusions. Okay? In terms of artificial intelligence, the reasoning can be implemented by means of logics, such as Boolean logic or fuzzy logic, for example. Then there is the learning. The learning is a human capability that improves the performance of human starting from observation about the world. In terms of AI, machine learning is the artificial counterpart of learning, where a computer observes some data, build a mathematical model of this data, and use this model as a system to predict new information. In particular, typical tools for machine learning are neural networks. Then we have the last part of AI, problem solving. Problem solving solving is useful when, in order to solve a problem, it is not enough a single step, but we need a kind of sequence of planned steps to arrive to a final goal of the problem, starting from an initial state. In particular, in artificial intelligence, a system performing this operation is named a problem solver and typically is used in optimization context. Okay? These are three areas of AI, and we would like to understand if these three areas of AI can live together quantum computing. Okay, as said so far, quantum computing can be seen as a kind of alternative computing paradigm that, using principles from quantum mechanics such as superposition, entanglement, interference, can introduce a kind of massive parallelism in computation. Okay? But why it is important to discuss about quantum computing? There are two main reasons: a kind of technological reason and a computational reason. Because in the future, it could be not more possible to further reduce the size of transistor in a CPU, and this could make not valid the Moore's law. Okay? And we will not be able to further improve the performance of current high-performance computing system. But from the computational point of view, currently there are some problems, such as the integer factoring problem, for instance, that could be solved by means of quantum algorithm better than their classical counterpart. And it means that quantum computing could make not valid the strong thesis of Charles Turing. It could be the first computation paradigm that could not be simulated by a Turing machine in polynomial time. So these are the two main reasons for quantum computing. But however, as we know so far, there are some problems in quantum computation related to the noise and the limited size of qubits that we have available today. And so, starting from this discussion about AI and quantum computing, the question is, can quantum computing and AI merge together in order to take benefit one from the other? From one side, we can introduce the concept of quantum enhanced artificial intelligence, where we would like to use the computational benefit of quantum computation to design and develop new reasoning system, new system for machine learning, and new system for problem solving that are more efficient than their classical counterpart. From the other side, we can use classical artificial intelligence techniques to try to improve the performance of current quantum computers, okay, by means of artificial intelligence. So we have a kind of bidirectional in relationship between quantum computing and artificial intelligence. Now we start with quantum computing for AI, and I will introduce you with some algorithm we developed here in this department. In particular, we worked on quantum reasoning. We introduced an algorithm that speed up the inference process typical of human reasoning. And thanks to this algorithm, we will develop control system or decision support system capable of working on big data in an efficient, interpretable way. Particularly, we have developed the quantum fuzzy inference engine that is an algorithm able to run fuzzy rules on a quantum computer. What are fuzzy rules? Fuzzy rules are rules that allow us to control a system in a linguistic way. Okay? So, for instance, in this case, we would like to use a quantum computer fuzzy logic to control an inverted pendulum. Okay? We would like to find the equilibrium position of that pendulum by means of these linguistic rules, taking into account two variables, this angle and the angular speed of this pendulum, in order to set the value of the current of an electrical motor that we have here at the base of the pendulum. And here we can see the result of our experiment. We have implemented this controlling on a classical computer and on a quantum computer. And we can see that both classical computer and quantum computer are able to find the right position of the pendulum by firing the previous rules. Okay? Here you can see that in particular the quantum computer is able to reach the position in a quick way that is with respect to the classical computer. Why we have introduced this algorithm? Because in a fuzzy system, the number of rules grows exponentially with the number of input variables. And for this reason, the classical algorithm to solve this problem is an exponential algorithm. Thanks to our algorithm, we have a polynomial time algorithm on a quantum computer to infer the fuzzy rules by means of a quantum oracle. Okay? And this is a kind of very important computational benefit of this provided by this algorithm. But another important benefit is that we are able to program a quantum computer by using linguistic rules. Okay? So we bypass completely Hilbert space and the complexity of quantum computing because we are able to run this rule on a quantum computer. Okay, now I will show you how to use, thanks to this algorithm, we have been awarded with the Fujitsu Quantum Challenge Award, and the University of Naples has been the only university to be awarded with this award. Okay? Now, I would like to show you how it is possible to implement evolutionary algorithms on a quantum computer. Because so far we have implemented different evolutionary algorithms based on quantum computation that are able to solve optimization problem by using the quantum parallelism. Okay? What are evolutionary algorithms? Evolutionary algorithms are optimization algorithm that, starting from a population of candidate solution of an optimization problem, evolve this population step by step in order to identify the optimal solution of the problem. Now, our idea is to use superposition to move all these points in parallel toward the optimal point of this problem, the optimal solution of this problem. Okay? And Also, in this case, we have implemented different algorithms. We have implemented the first genetic algorithm on a quantum computer that has been awarded by IBM with an IBM Research Program Award in 2021, and currently is used to solve optimization problems. Now, the last part of our research is related to quantum machine learning, where we would like to use quantum computation in order to improve the performance of a current system for machine learning. How it is possible to implement quantum machine learning? By means of variational quantum circuits. Variational quantum circuits are some circuits where gates are based on some parameters, then to optimize by using a classical computer. So they are very similar to neural networks, but they can be implemented on quantum computers. And also in this case, we are using evolutionary optimization techniques in order to optimize variational quantum circuits and implement quantum machine learning. Okay, so this part of the presentation was related to the presentation of some quantum algorithms for artificial intelligence. Now I would like to show you how classical artificial intelligence can be used for improving the performance of quantum computation. Yeah? In particular, we are working on the usage of classical artificial intelligence techniques to mitigate and correct quantum errors, to optimize quantum circuit, and to implement control system for quantum processor. So this is our idea. And in particular, we are using genetic algorithms, neural network, and in particular, fuzzy clustering to mitigate the error in a quantum processor. So by means of this technique, we are able to detect different error patterns in a quantum processor and to perform some mitigation in order to have better performance from the processor. Moreover, another problem on which we are working on is related to the quantum circuit mapping, because when we implement a quantum circuit, the bits that we see here, the qubits that we see here, are not necessarily connected in the processor topology. And for this reason, we have to find the optimal map between the logic qubit and the physical qubit. And in this work, we use the deep neural network in order to perform this mapping. And also this approach worked in a very good way. Okay, so we can say that the integration between AI and quantum computing could be very useful, because from one side, quantum computing can improve the performance of current techniques for artificial intelligence, and from the other side, artificial intelligence can be used to try to speed up the development of adequate quantum technologies. Okay, thank you.
Thank you, John. Yes, we have to be late, so I think we will.
Just a quick question.
Okay, just one question. Don't want the one. It was really for start with.
No, as a matter of fact, it's only people, because we are a little bit late, and also people who get planes and trains. So we conclude. So with Giampiero, we get to the conclusion.
Yes.
Thanks so much.
Thank you. Thank you very
much. Just a few words from me and Giampiero, just to thank all of you. It's been really a privilege to have all of you here, especially those who are coming from far. And we really appreciate, and probably some kind of party that's not really a conference, it's an aggregation of ideas and friends to be together. And for us, this computer is some kind of promise for the future. It's not another point, it's just a starting point to do with the community together, Italian and European community. And so to be together as we have done up to now. This is the result not of a group, of a person, of people, it's the result of talent system inside Europe to be competitive. We have put together a lot of different things, and we are growing together, both in terms of no. So I have another, so time to thank. We have thank all of you, and Matteo and Alexa have been really great. So the foundation has been great in supporting us, and then our young people really amazing, and really thanks to all of you. And then before passing the word to that, there are a lot of seniors and a lot of young people. We hope that we have given you some kind of overview, feeling, at the end you learn how to get support. It's a good idea, and that's basically the feeling, something which goes very fast. And if you're doing quantum, you're on the right track. That's the general feeling. So from me, Giampiero, and our group, and obviously yesterday you met the director of the university, the major of the city, for full support, and thanks to all of you for being here. Allora, no, io voglio dire. No, non c'è stato registrazione, basta, non lo so perché poi fai altro. No, interrompi la registrazione. Non lo so,
Sentiamo, grazie a tutti.